Welcome to another coding session where we are working on a new programming language. So this is the third session, and let's just have a look at what we already implemented. So you can currently do this. You can define functions like this, and for example here we have the main function which calls the isLess function, and the isLess function compares two numbers, and compare is a built-in function. Oh yeah, let's actually change that. So when you run this program, what basically happens is you get this sort of representation of the program that already has a lot of information inside. We see that the main function gets compiled for ints, that's just hard-coded into the compiler. And then here are a list of expressions that need to happen. So we have the parameter a, which is of the type int. We have something where we don't need to do anything at runtime, but we know the type of that is the isLess function. We have a 1, which is also known at compile time, so at runtime we don't need to do anything. And then here we call the isLess function with two arguments, the parameter and the constant 1. This returns true or false. And because this isLess function is called, that means that it's specialized up here. The isLess function is specialized for the types int and 1. Numbers are also types because if they are known at compile time, they can just basically be treated as constants everywhere. And at runtime we don't need to save anything. Like at runtime this can be compiled to a function that only accepts a single int and just checks if that int is smaller than 1. So basically the size of this compile time known int is 0 at runtime. Right, so we have the parameters and we call this compare function, and then we switch on the result. And the compare function again is down here, and this is actually a built-in function. It's down here, but this calls the built-in compare function, which is built into the compiler. And you can see this contains an instruction, which is basically like a built-in but at a lower level. Like this is something where we know that the types are correct. This is something where we know that this is basically something for the next stage of the compiler. When we compile this entire thing to C, then each of the instructions basically gets converted to something different. Alright, so the question is basically what do we want to do in this session? And I think there are multiple angles we can take. So one thing that would be nice is to have more built-ins. Currently only add and compare are implemented, and there exist a handful of others, like only things that work with integers, because that's basically the only type we have right now. And what we really want to do is maybe add some more built-ins. For example, one for crashing the program if it's reached. Something like a panic or crash or something. And maybe even add more types. So not just have ints, but maybe also add string constants, like string literals you can write in the language. And then, concatenate strings and so on. So that basically we can create a hello world program. That would be nice. Right, then the third thing is we should work on compiling this to something that can actually be executed. Not just have a nice terminal output that is type checked, but also convert this to something we can use. For example, to C. And the next thing after that, or even before that, would be to add some more error handling and think about how, currently if you just write some nonsense in here, I can even show you. It will just say, well, okay, there's additional garbage on this line. But there are some cases where it just tells you, hey, something is wrong here, but you don't get any information about like which line contained an error or something like that. So yeah, the error handling is bad right now. We need to improve that. Yeah, that's basically the plan for today. Okay. Yeah, before this language was named Kamin, I renamed it to breakfast. Yeah, I did that off screen because I had to like rename the GitHub repo, and yeah, the only thing I did is basically this. Remove the nodes and instead add a readme with this. Yeah, I still need to think of a file ending because currently the files, they are just they have the ending .km, which works for Kamin, but for breakfast we need something else. And .bf is already taken by brainfuck, which is, I don't want to say popular programming language, but it's like not a lot of people program in it, but it's like the basic starter example for how to write a compiler or how to do stuff. It's very, very simple language. Yeah, and I adjusted the imports. That's basically everything. Okay. Cool. So I guess let's start by adding more builtins. For example, one for crashing the program. Yeah, this, like if the compiler sees this, it will just convert it into a crash instruction. So instructions are things that exist at runtime, basically, like built-in functions that exist at runtime. And yeah, we should also add this to this list of all built-ins. Built-in crash. And I think that's basically it. Yeah, I think if you do built-in crash down here, yeah, we need to think of how we treat arguments. Should probably accept a message or something, but it kind of requires strings, so that's another reason to implement strings. All right, we need to implement that, which means in here when we type check things, yeah, when we find a crash, we expect one argument. Yeah, we emit a crash instruction with the arguments. And oh, what's the type of this? Basically, it's guaranteed that this, never returns. So let's, like for now, let's just return a never symbol, but this is wrong. Right, so here we see that, yeah, the type of this is the never symbol, crash instruction, that works. But it's not correct. Yeah, I think we actually need to add a new type. Because I'm thinking of the following scenario. Let's just have crash with a message is built in crash. Yeah, down here when we have, we compare two numbers and we are sure that they are not the same number. for example, we should be able to do something like this. Yeah, here crash, they are the same number. You know, oh, right now, just crash. I don't know, something. The type of this thing should still be true or false, not true or false or never, like it is currently. Yeah, it's true or false or never. But never is kind of a special type. The compiler needs to know that, hey, this never completes. It's guaranteed to never complete. So we need to add a new type. And let's call it never. Because, you know, if you have some expression and the type of that is never, you know that it never, like this type will never exist. Like, okay, an instance of this type will never exist. There are 0 instances of this type. Okay. And actually, I think this is a nice moment to introduce like the sharing the screen. So there's a thing called type theory and category theory. And it's basically a way of looking at types and functions that convert between different types. Yeah, this is the screen, right? Okay, so the way it usually works is that you have some kind of unit type, which is a type with only one instance. And this is like in Rust, for example, this is just opening parenthesis and closing parenthesis, like an empty tuple. In C, this is called void. In Martinez, okay, yeah, let's actually write down. You know, there's void. In Martinez, there's nothing, which is just an empty struct, basically. And this unit type is a type that basically tells you nothing about the result. Like, it doesn't have any information. At runtime, this is 0 bytes big, because there is only one instance of this. Yeah. Then there's a never type. Oops. And the never type, okay, let's actually write down, you know, one instance. And the never type has 0 instances. And in Rust, this is, you know, you can write an exclamation point, I think. Yeah, I don't know if it's standardized yet, but I saw that in some code at least, that you have some code, for example, if you have a result, but the error value never gets constructed, then you have a result of, I don't know, a number like usize and exclamation point. And it basically tells the compiler, hey, this type inside this can never actually be reached. And it's kind of interesting to see how those types propagate. Like, okay, in Martinez, this is called never. And I think C doesn't even have a concept for that. I think there are some like, I don't know, GCC extensions or something where we can annotate a function with no return, I think. That's what it's called. Yeah, maybe there is actually no return. Right. And yeah, these types, they compose in interesting ways. So the never type, for example, if you have a struct with where one of the fields has the type never, then the entire struct can be treated as having the type never. Because in order to construct a struct, you will need an instance of each of the fields. and the never type has 0 instances. So there are also 0 instances of the struct. And yeah, this mapping of, we have these types to categories. Actually, let's stop at this. This is like enough to know about, and I'm not an expert in this, so this is more like half knowledge. Yeah, I think this is fine. So we basically have a unit type and some sort of never type. Yeah, for a unit type, we can actually think about how we're going to represent that. For example, if we have a print function, what does it return? We could say that it just returns a nothing symbol as a convention, you know? Yeah. But I just want to show how this is implemented in Martinez. So in the standard library, right, there's the nothing type, which only has one instance, and it's an empty struct. And there's a never type, which has 0 instances, which is an empty enum. Yeah, that's kind of beautiful. Right. So yeah, we have a never type in here. And yeah, let's just okay, actually, what? So the one thing I wanted to show with never and unit was that you can basically calculate with these types. So for example, if you have an enum that is foo or bar, you know, so 2 instances, and you have an enum that is true or false, also 2 instances, then these can be treated equally. Like you can have an isomorphism, basically a mapping from this type to this, where you can map each instance of this type to one of this and the other way around. So they kind of have the same amount of information that they give you, because each of them has 2 instances. And what structs do, so if you think about it, struct has some fields like A, B, C, and it basically is like a product type. So for example, if you have a bool in here, which is true or false, and you have a bool in here, which is true or false, and let's just remove the C, then the first bool can be true or false. There are two variants. And for each of those, the second bool can also be true or false. So you have 2 times 2, which means 4 variants. And if you have a third bool, then you have 8 instances of this struct. So basically a struct is like multiplying the amount of instances that you have. While an enum is, an enum has named variants, something like A, and then this contains a bool, and B, contains a nothing, a unit. And an enum basically adds the types. So in an enum, it can either be A with, then 2 possible instances, true or false. Or it can be B with 1 possible instance, unit or nothing. So this can have 3 instances. Whereas this up here has 2 times 2 times 2 instances, 8 instances, and this has 3 times 1. So now it gets interesting. If you have a never, for example, which has 0 instances, well, if you put a never in a struct, then you see that the entire struct also has 0 instances. So it's a type that has the equivalent amount of information as just the never type itself, because the struct also can never be constructed. And in an enum, if you have a never in here, that's not a problem. Like, you know, then you have, oh sorry, this should be plus. So before it was 2 plus 1, and now it's 2 plus 0 instances. Because this enum is either A with a bool inside, or it's B with a never inside, but there are no instances of never, so it can actually never be this variant. Right, so this enum is kind of equivalent from an information theoretical perspective to the bool, or to foo or bar. And the struct is, you know, it has 8 instances. It's equivalent to all of the other type that have 8 instances. Now you can kind of calculate with these. So let's assume you have a user. That's too complicated. Let's say you have, let's just say you have a struct foo, which contains, I don't know, an A, which is a bool, and a B, which is, oh, actually, let's look at, let's say we have our toast. You know, the entire program gets converted into this toast tree where each thing is like, oh, I'm a number, I'm a definition, I'm, I don't know, the file, I'm something else. I'm a switch, for example. And what if we want to save some additional information, like, for example, the location in the source file where this came from? Then we basically could say, well, we have our enum toast, which is either, you know, it's an int with an int and, well, let's write a tuple like this, an int and a source location, or it's a definition with a definition and a source location, and so on. And this has the same amount of information as if we would say we have a struct toast, which contains a source and, you know, some information about which kind of toast it is. So I don't know, toast kind, and then we have an enum toast kind, which just tells us it's an int with an int, or a definition with def, and so on. And these two things, they are again equivalent or isomorphic in the amount of information that they carry. And this is mirrored in mathematics by the fact that this up here, if you calculate the amount of information, it's basically, you know, the amount of information that toast has is an addition of all of the cases. So the first case is a tuple is similar to a struct in that all of the subfields have to exist there. So this is the amount of information that you get from an int and the amount of information that you get from a source multiplied. Because again, structs, they multiply things, and enums, they add the amount of instances that exist. So this is int times source. And the second variant is a definition. So this is def times source, and so on. And yeah, you can see that this is equivalent to just having a struct with a source multiplied by this other field, the toast kind, which again is an int or a definition. Whoops. So you can basically factor out types and basically kind of calculate with types. Yeah, that's just a theoretical understanding of how those types compose. And actually an explanation why we need the never type. Like this, for example, if you come from C or something, this might seem like a weird kind of, weird invention. Why do we have this never type? It just seems so out of this world. But it actually makes sense. If you want to have this principled approach of reasoning about types, looking at the amount of instances they have and calculate with types, and you kind of need this type that says I have 0 instances. That's very, very fundamental. Yeah, that's why we need a never type in our language, so that we can correctly basically calculate or type check the result of something like a crash built-in. Okay, yeah, that's enough derailing of this session. Let's look at the types. We have the never type, and that means that down here this can just have the type you got type never, which basically says, hey, this expression will never complete. And yeah, there are some errors here, because you need to be able to print this type. Hang on. Yeah. All right. Now the cool part. Joining the never type with other types. So yeah, if this is a never type, that's it. Well, that's it. We switch over A, the first type. And if this is a never type, we can just return the second type. Because again, this join is like an addition of types. It's basically called when you have a branch and when you have a switch and all of the branches, they evaluate to something else, and then you want to join those types. So yeah, if we add a never type, which is the type with 0 instances, it's like adding 0. It's doing nothing. Do we need to handle this in the other cases as well? I think so. Yeah, for example, we can join a compile time int and never. That works. That's just, A. Some A. And that's basically the same here. And the same here. Yeah. And the same here. I don't like that it's like the same behavior in each case. We can probably have like a special handling for never types, maybe. Because this is a property that's unique to never types. So if A is never, return B. If B is never, return A. Yeah. And then we don't need these. Oh yeah, and this is actually unreachable. Oh, okay. Okay, yeah, I like that more. Cool, so we can join types. Oh yeah, and let's actually look at our example. In the equal case, we just crash, and that means that in here, well, we have a switch, which either evaluates to true, or never, or false. And these get joined to true or false. Beautiful, beautiful. Okay. Yeah. Actually, let's commit more frequently. So here we support crashing. Yeah, that's kind of a bad example, but, you know. Support add crash builtin. Cool. Then the next step would be to implement other built-ins. So currently we have add, subtract, multiply, divide, compare, but they don't actually, you know, currently we only handle add, compare, and crash. And I think we need a more reasonable way of, like, for example, in each case we compare the amount of arguments. We need to factor that out somehow. But before we do that, let's just implement the other operations, and then you know what? Like, let's do that first, because yeah. How do we check the? Wait, do we check the amount of arguments that we pass down? I hope. No, we don't. Okay, so right, if we call a function, okay, we have an expression which is a call down here. We have a receiver, we have all of the arguments, and yeah, if we call an enum, like a symbol, that's fine, okay. If we have a function, we basically want to check that the amount of arguments matches the expected amount. Right, so this is fun, which is, an egg dev fun. Let me look at the egg. An egg dev fun is probably this with params, and that has a len. So fun.params.len should equal args.len. Called fun name with this many arguments, but it expects, yeah. Well, okay. Cool. Yeah, so this should now get called, right? Yes. Called is less with 3 arguments, but it expects 2 parameters. Nice. And for built-ins, we want to do something similar. So I think we'll just add a function, num apparams, takes the built-in, returns an int, and it just switches over the built-in. Add returns 2, sub returns 2, multiply returns 2, divide returns 2, compare returns 2, crash, expects, they don't return 2, they expect 2 parameters, and crash expects 1 parameter, the message. Okay, cool. I like that. Nice. Right. So let's fix this. Nice. Built-in compare. Let's built-in compare called with 3 args. Oh, right. So in here, we have a built-in. We want something very similar. So the built-in, we can get the parameters built-in dot num-params, which is what we just implemented, called stuff with stuff, and stuff is bad because stuff. Okay, so we check that the amount of arguments is correct before lowering the built-in. Yes, called built-in compare with 3 arguments, but it expects 2 parameters, which means that down here we don't need to check this. What? Okay, that's so much better. So much better. Okay, and we should also check the types. Make sure that the types are correct. Yeah. Oh. Okay, you know what? Let's try something. Built-in add of 2 and 3. What's the type of that? Is that a 5 or is that an int? Yeah, call built-in add. No, yeah, I know. Yeah, the return type is int. This should probably be 5. Yeah, if we call built-in add with the types 2 and 3, we already know the return value. We can constant fault that. Yeah. So we kind of need to check if archetypes. Oh, you know what? Let's say A is A type and B type, and yeah, archetypes get 0, and we have the B type, which is this. If A type is a Comptime int of some A, then if the same holds for B, then we just constant fault them. Oh, that's nice. So what we do here is we say body dot push yeah, yogurt value dot Comptime yogurt type dot Comptime int of a plus b. Oh. A plus b. Yeah, the result of this is ignored anyway, so let's just call ignore. By the way, ignore is defined in the standard library as a function that takes anything, any parameter, and just returns nothing. Okay. Yeah. So I basically want to have an else, but this is a nested if. It's one if and another if. And I don't want it to just apply to the inner one. Oh, I don't know how to do this elegantly. You know, there are no labeled breaks or something in Martinez. There are no... We could factor this out into a function. I don't like this. I don't like this. Okay. Yeah, let's factor this out into a function. It's probably overkill for what we have right now, but over time we will add more built-ins and yeah. Okay, so this kind of, it accepts like none of these, just the, like not a yogurt or an egg or something. Yeah. It just calls, yeah, it just accepts a yogurt bodybuilder. Oops. Yeah. And then args, which is a slice of yogurt ID and archetypes. Yeah, kind of like this. And then the main switch can be down here. And actually it returns a yogurt ID, the ID of the last expression. Like the expression that should be returned. Which means that up here we don't need to get the last expression, but we can actually say, hey, let's just take the built-in, convert it to a yogurt using the body and the args and the archetypes. Yeah, kind of like this. And this is what's returned. It returns this. And then, right, here we directly have a yogurt ID. Kind of like this. Yeah. Cool. Okay, so we handle the Comptime case separately and just immediately return. And otherwise we emit an add instruction that, like, you know, adds those numbers at runtime. I like that. Then we have a compare instruction, which should probably do something similar. So if this is a Comptime thing and B is a Comptime thing, we'll just do the comparison right here. So this, let's just compare A and B. If it's less, then oh. Okay, if you create a symbol, how does that look right now? Up here, oh, it's just Comptime with the symbol, of course. So yeah, this is Comptime. Oh. Okay, so let's go with this like this. We push something to the body in either case, and we return that. Yes. And the value is always Comptime. The type is always a symbol, sorry, an enum. Yeah, just like down here, with a map, where a string, which string depends on stuff. It's less. Oh, yeah, let's actually first do this. Yes. Get the correct symbol, which is less or equal greater. Yeah, then here we can just have a map from symbol to an empty slice, like this. Is this, yeah, this is not totally beautiful, but yeah, this is fine. Cool. Yeah, we have compare, which takes those and does that. Oh, we also need to check that both are ints. So either an int or Comptime int. Let's actually add an isInt for that. Keyword type is in inty, because it's not, you know, it can also be a Comptime int, which is not the int type, but it's inty. That's basically it. Yeah, and then if they are not both Comptime ints, then we basically just check a type is inty, or, you know, panic called compare with non-int, and same goes for b type, and of course also for the add function. Except we say called add with non-int, like this. Cool. Let's check if it works. Oh, nice. So we have the add function, which takes a 2 and a 3, and it returns a Comptime 5. And then in the main function, when we call this, the type of that is also directly inferred to be 5. Cool. Very, very cool. Okay, we have, we check the amount of arguments. We check the types of parameters. Okay, for add and compare, not for the crash function, where we like to do check it's a string, but we need strings for this to work. Okay, right. What's the next thing? Okay, let's commit this first. Here. Check number of arguments given to or did I just commit test? Oh, sure. Okay, that's cool. I think that next let's add some interesting built-ins, namely type operations. So I want this language to be like Zig, in that you can just ask, hey, what's the type of this value? So you can ask, I don't know, type of A, and this gives you some opaque type type value, which you can't use for anything. You can compare it with other types possibly, but apart from that, yeah, it doesn't do anything. Yeah, and then you can do type info on a type, and that gives you info, so that returns info, which you can switch over. So you can basically check, is this an int? Is this a symbol? Is this an, well, not symbol, is this an enum? Is this a Comptime int? Basically surface the information that we already inferred about the type in the program itself. And we probably also should implement like unwrapping the payloads of symbols. You know, if you do something like this, we can't get this out currently. Yeah, oh, it's an enum with variants, or you know what. So I want this to exist in the language, because that allows some crazy things. You can do, I don't know, we format some value, or even just, you know, we add an A and a B, and then we could do this and be like, hey, if it's a Comptime int, well, then we just, you know, basically add them directly. We could even have is inty in the standard lib, and have, yeah, like it's assuming we also have like a Comptime string and string. Yeah, we could basically do this. You know, you can't actually do anything with a tiny bit. Yeah, I don't know. Let's do it like this. And for example, this would be implemented somehow. We should add like default cases or else or something. Yeah. And you can have a is stringy. Like using underscore for ignored things. Yeah, and then in here we could check this could probably just work on types. Yeah. Type A is that, type B is this. And then you could just say, well, if, we don't have an if, maybe we should add that too, is stringy A, and, well, you know, add. how this will look, but something like this. You know, if they are both stringy, then we just call, I don't know, standard string concat with A and B. If it's false, then we do other stuff. Then we can check, are they both integers? Then we call the standard int add or something. So you can basically do compile time reflection on the types. And later on, if we have something like structs, we could even check, I don't know, what is the type of this thing? Is this struct with fields? We could, for example, allow that if you create some sort of type with a special symbol named opaque, for example, and then there's a struct. I don't know how this will look, but you know. And here you define a member called add. We could also say that the plus operator just looks like inspects the types at compile time, and if it's an opaque type with an add function inside, then it uses that function. So this is kind of like not like I don't even know, like an interface type, maybe, like a type that defines its own behavior, and you could implement that, and it shouldn't have any runtime cost because the add function would just be a compile time known function. So the types, the values that you pass around, they don't actually contain function pointers and so on, but they only exist during compile time. So part of the function, part of the type is just known at compile time. That would be super cool. Right, but before we do any of that, we need this reflection thing. We need to say what's the type of, and I want to have information about a type. Right, so let's maybe turn this in some, do we have playground file or something? We have a language file, okay. Ah yeah, here's an example with format where we also check what's the type of this, and then based on the type we do different things. Integers have some hard-coded way of formatting them. Structs can be formatted differently and so on. Right. So what we need for that is to have a type of function and then a type info function. We could even, we could think about merging these into one type info function, which takes the value and returns information about the type of the value. Yeah, Zig has split this into first getting the type, but a type is basically something you can't do anything with this. In Zig you can use this where a type annotation is expected, but apart from that, yeah. Right, so I think for now we will just do it similar to Zig, just because that's, they probably thought a lot about this and came up with something reasonable. We can merge them later on anyway, if we need to. Okay, so type of and type info built-ins are what we want, which means we basically want this to work. So type of a value calls built-in type of the value. type info of a type calls built-in type info on that type. Yeah. And let's just write a format function. I know we don't have strings, but it will just say type of, and then switch, sorry, like this, switch on the type info. And it will just return a symbol that represents how this will be formatted. So either int or we only have ints. Int or other. Why not? Yeah. We want to be able to do this. So let's see where this currently fails. Probably, yeah, there is no built-in type of. We need to add built-ins, type operations. So we have two of them. We have type of and type info. Type of accepts one argument of any type, and type info also expects one argument of any type. Right. So then in the okay, you know what? Let's actually merge these. I think that's easier. Let's just say we have a type info built in, and then because otherwise we need a type, and it may make sense to have that at some point, but for now I think it's fine like this. Yeah, you just say type info on the value, and then you can do stuff. Okay, so yeah, yogurting a type info. Also, we need to add this to the list. Yeah. Oh, but this instruction, this built-in only exists at compile time. At runtime, there is no type info instruction because at runtime there exists no like metadata stored about the types. If you have a value, it only contains the data, not any metadata about its structure. So we don't need to add anything. After the, like in the yogurt, adding this type info doesn't have any effect on what later compiler stages need to do. Right, so this just says let's get type. Nice. And yeah, we don't special case anything, we just have a big switch, I think. Well, we can do some stuff, I guess. So yeah, this will be an instruction. Sorry, no, what am I doing here? This will be similar to this right here. Yeah. We calculate, like we have a symbol based on what kind of type this is. And yeah, in here we basically need to handle all of these. Oh, red never also exists. Cool. Okay, so we have a symbol, and then we push that. Basically, we just push that symbol, and that's it. Okay. What? Okay, so type info on 5. It returns the symbol Comptime int. And then when we call format with 5, it just returns int. What? That is crazy. That is super crazy. That is kind of mind-bending, to be honest. Okay, what if we pass something else? In format and a, for example. This should still return int. And it does. Nice. Okay. Wait, what other kinds of types were they? We have complement and enums, right? So if we pass in foo, I think this crashes currently because this foo is not handled yet. Yes. Switching on enum, but enum is not handled. Well, yeah, we could. I know all of the error reporting is horrible, but yeah, this switch right here, we need to handle enum. So if this is an enum, we just return other, for example. What? That's kind of cool. So we call the format function, and it just returns int or other. But like, of course, you can imagine that later on we will actually have, you know, like formatting code, like ints get formatted using some int formatting function, and with enums we have the variants up here, and then in here we basically have a switch, or like a, you know, where we basically switch over the value, and based on the variant, I'm not sure how we do that, but there is definitely a way to do this. Although there will be a way to do this. Oh, that is super cool. Super cool. I love this Comptime thing, that you basically can do anything at compile time. That's kind of mind-bending. Okay. What else? We have more built-ins. We have a type info built in. Yeah, I think it would make sense to either work on strings next or on unwrapping things in switches. And I think we'll go with the both of those are interesting. Let's go with strings first, because then we can actually have like a small hello world. Yeah. Cool. Nice. Yeah. You know what, let me take a quick break. Eat something and then we'll continue. Break. Oh, right. Nice. we have a break. Okay, see you then. Bye. All right. So, yeah, next up, let's implement strings. Right, so I think we need to add something in the parser. Yeah. You know what, let's just try to have a string literal here. Hello world. Just like that. And just see where the parser fails. Right, expected expression. Right, so this is an expression, which means in here where we have, you know, parsed expression, we basically want to also allow strings. Strings are actually an atom, so something, you know, basically an expression without white space in the middle. Well, strings can have white space, but they're more like they are enclosed in quotes, so it's not as bad. And strings should be a normal literal, similar to an int. So we'll have a string. And then, alright, we need to be able to print strings, which means if we have a string, then we'll print, you know, quotes, and inside of those quotes the string. And when parsing an atom, we try to parse an int, we try to parse a string, and if that works, then we return the string. Yeah. Cool. Yeah, parse string doesn't exist, of course, so that would, we would have to create that. This is not like parse int. Well, I mean, we can check the start. Actually, let's maybe first adjust the signature. Then we get the current character from the parser. If we're at the end, then, you know, there is no string to parse. Also, the character has to be a double quote for this to be a string. Otherwise, we're like, nope, no string here. Then we save the start, which is the current cursor. Then we do this. If the input ends, then that's an error. String doesn't end until input end. I don't know, something like this. Right, so if this character is a quote, then we break. Otherwise we advance. Okay, yeah. And then the end is the cursor. We consume the quote. And yeah, then we just return sum, parser, import, substring from start to end. Okay. That should be it, basically. Let's see what happens. Alright, so in the next compiler stage, in the egg, we switch over the toast things. Yeah. We we just added to do there. Okay, so this didn't work. Why didn't this work? Hang on. We have the bacon. Okay, sure. But then there was this. Converting this to a toast. Additional garbage online. Cursor is 6. Cursor is 6. Oh, right, no, that's where this is. Additional garbage online. Let's first find out which one it is, but it is, yeah. Okay, so it's this down here, which means, okay, basically we have some bacon, and we say consume white space, and then there is other stuff. Right, so parser expression, that's kind of weird, right? This is super weird. Cursor, right. Let's also print the expression that we have so far. Oh, okay, so we have a call. Oh, I see what's happening. Right, so yeah, here we check that we have a double quote, and then we loop until we add a double quote. So of course we need to advance the parser up here so that the first double quote doesn't like immediately start a string and then also end the string. Yes, this looks amazing. So main is a function, that takes an A and it just has a string literal inside. Cool. Right, on to the next stage, the expression graph. I think we just have a string expression up here. Yes, we need to be able to print that. Almost. Yes. And I think that's basically it. I mean, the next compiler stage, yeah, the next compiler stage will complain. Because here we basically, it's compile time known, so we need a Comptime string and a string, similar to how we do this with the ints. Right, and then, yeah, switching is also similar. And this switched around, doesn't make any sense. Right, so they can be printed here. For strings, we also print this. Oh, by the way, in the egg, when printing those, we should also print. Oh, we can't even say debug. Yeah, debug also prints quotes around that, but it also like replaces new lines with \n and stuff like that, which is kind of, we don't need that here, but I think it's cleaner. Okay, yeah, if it's a string, we just print string. And then when, yeah, we need to be able to convert those. So if there's a string literal, this will be a Comptime value, because it will be a Comptime string. What's done here? Right, when we join types, we need to handle the case of a Comptime string, a string, and this will be pretty similar to how ints work. So if b is a Comptime string, b string, then basically we check if they are the same string. If so, then this is just, you know, a Comptime string. Otherwise, it's not Comptime. We just know that it's a string, but we don't know which one. Right. And if b is a runtime string, then the entire type will also just be runtime string. Next, if this is a string, then we check that b is either a Comptime string or a string, in which case the type of that would also just be string. Otherwise, the types can't be joined. Right, and now we get to the type info built-in, which basically, I mean, you know, we just print symbols. Boom, handle string. Handle string. Was that? That was here, right? Oh, right. So, yeah, that conversion is pretty obvious. Nice. That's basically it. We just added strings. So we have the egg, and then here's the yogurt, which is, right, this is the main. Yeah, this is the main function. And we see that we have a Comptime value hello world. Okay, so let's try to do something great. Let's actually try to implement this format thing. Yeah, Comptime in, you know, ints will just print something like an int. Or Comptime int. A string will just print the string, and similar a Comptime string. So the return type of format will always be string. Just the content of the string depends on the value. Yeah. So here we call well, yeah, we call hello format with hello world, and we can see that in the main function, the type of this, the result of this is hello world. But we can also say format is in 5, and then boom, we have a string that contains a Comptime int. That's quite cool. Oh, and actually, let's define the. Wait, we support plus, right? Something like this. We don't. That's weird. Oh, I know why. Hang on. In the toast, yes. When we pass like an identifier as anything. Oh, I see. Let's maybe identifier Charles. Yeah, here we say identifier and we check that they are upper or lowercase, which, like, yeah, obviously that doesn't work. I want to be able to use like plus, minus, times, slash, you know, some symbols as identifiers, so that you can even mix them with this. So this should be a valid identifier. We don't really have operators anyway, so you know you can just define a plus function like this instead of relying on these names. Yeah, I mean, of course, percent doesn't work because that's a switch, and equals doesn't work because that's a way of defining values, defining variables. But many other characters should work. And yeah, we could do something like char is we basically have a fixed set of characters we want to allow. Let's actually unify this into something like identifier chars dot contains char or break, and this is a string of all of the allowed characters. So A B C D E F G H I J K L M N O P Q R S T U V W X Y Z. Yes, and then the same in lowercase, and then underscore, plus, minus, star, and divide. Cool. And then for the name, we don't ensure that this is a, like, okay, I think the question is this a name or is it a symbol? I think symbols should still start with an uppercase letter, but those other names can be anything except uppercase symbols. So as long as this is not an uppercase symbol, an uppercase letter, I think we're fine. Right. Let's also check. Yeah, first we try to pass ints. All right. Yeah, should be fine. At some point we may want to allow numbers inside of those identifiers as well, but we'll get to that. Yeah, this is a Comptime int, and that seemed to pass and work. Okay, so what I really wanted is to basically overload the plus operator, so it could look at the type of A and then do different things. If it's a Comptime int, it should do built-in add of A and B. Same if it's a runtime non-int. But if it's a string, it should do built-in concat or something like that. Yeah, we need a built-in for concatenating strings. Else, oh, this is interesting. Crash tried to add weird types together. Great. Cool. Yeah, built-in concat doesn't exist, so we need a new built-in. This built-in is called concat. It's a string operation. Yeah, operations, because we may add other operations as well. And yeah, the built-in concat also takes 2 arguments. Great. Yeah. Unknown reference name crash, right? Because let's define that actually. Crash with a message is built in crash with that message. Cool. This actually works. Crazy. Let's use that. Let's say we have 5 plus, no, sorry, not like this, plus with 2 and 1, and plus with high, and well. Whoa. Yeah, implement builtin concat. We still need to do that in the yogurt, in the function where we implement the builtins. So we have the int stuff, and then if we want to concatenate things, we basically want to, yeah, we want to have something very similar to this, or rather very similar to this up here. Yeah. Yeah, we get the argument types. If both of those are compile time strings, then the result will also be a Comptime string. Yeah, it will just be the concatenation of those two strings. Right, and then we need to check, actually makes sense, if it's stringy. Yogurt type where we basically just check if this is a Comptime string or string. Okay. Yeah. Concat. Alright, we need a concat instruction as well. True. Because concat may need to happen at runtime. Boom. Whoa. Okay. Okay. So, you know what's amazing? We have the main function, which calls the plus function with different with operands with different types. So the plus function gets compiled multiple times. It gets compiled for those Comptime integers, in which case it just returns 3 at compile time. And we can even see that, yeah, the return type of this is 3. And then we call the plus function again with strings up here. And something totally different happens. Here we call the built-in concat function. And turns out the result of that is hello world. Wow. This is pretty cool. I mean, I just love how functions can, you know, instead of having of being forced to use generics everywhere, and you know, this feels very much like you can do anything at compile time. You can do anything. You can write a function that behaves differently for strings and for integers. Oh yeah, let's actually try to add weird types together. So foo and bar. Yeah, okay, this compiles currently. And you can see that this call never returns because it crashes. Because in here, when we call the plus function for foo and bar, we see that it actually just calls the crash function. Yeah, which calls the built-in crash function, which again has an instruction inside. Here, a crash instruction. Whew, okay. I mean, we basically we basically implemented compile time type reflection. I mean, yes, you can't really inspect the types, you can only look at what kind of type it is, but still. Let's try to what's next? We have strings. I think next we could either try to compile to something like C, or we could support enum payloads. I mean, yeah, we already support enum payloads, but support getting the payload. And I think that's a minor thing, so let's do that first. Okay, yeah, let's say I have foo3 and I switch on that and I check whether that's foo or bar. And basically I want to be able to unwrap this type to get the inner thing. Alright, so after the symbol we expect a colon, that's true, but that shouldn't be the case. Hang on, before I do anything else, let me just commit this. So in the test I don't want this right here, but apart from that, implement, what did we implement? Symbols, no, sorry, strings, support strings, add strings, yes. Comptime string through all of the compiler stages and concatenation. Okay, nice. Now let's look at this right here. So when parsing code, yeah, when parsing a switch, basically here, no, here, yes, for each case we pass a symbol and then we expect a colon. Yeah. Yeah, between those we basically want to allow bindings. So we want to loop, and we want to basically pass names repeatedly. Yeah, or if that doesn't work, we just want to break. Also, I want to consume white space. Yeah, something like this. Yeah, and in the end, but it's not supported up here, right? In a switch, we have cases, which is a toast case with a symbol, and it should optionally also accept params, which is a slice of string. Yeah, so we need the params, and to do that, we basically want to maintain a list of params. So then in here we can say, oh, I don't know, params dot push. Yeah, something like this. We optionally pass some params, and that's it. Oh, by the way, params is params to slice, sure. Yeah, then, I mean, we don't use those params right now. Exactly. So you can write something like that, but reference name B. Why is that called? Oh, right. Yeah. Right. So when converting the toast to egg, if we have a switch, then here we have the case bodies. Yeah, and we basically want to, you know, do this basically. Yeah, it's a body, and we want to be able to restore the visible things and take a snapshot of them. It's strange that we didn't do that before, actually. I think right now if you have something like this, and in here you define, I don't know, something, you could actually use that in here. That's not correct. Yeah, this works. This is horrible. Like in the up here in main. Yeah, in the egg. Yeah, this basically refers to something from the other switch branch, which is just cursed, totally cursed. So what we rather want is that for each case, whoops, we take a snapshot of the visible things. Oh, sorry, when converting them to an egg, we do that. Right, so for each case, we take a snapshot. And then after we, you know, compile the body, yeah, we restore the snapshot. So all of the, yeah, this is what we want. And then reference name bloop, because now this bloop is no longer accessible in here. Here we take a snapshot of what variables are visible, and then sure, new variables are defined, but then at the end those are restored. So here bloop is not visible. What we do want is for those bindings to exist. So basically before each case, yeah, we also need to basically compile some way of saying, hey, this is a binding of something attached to the symbol. So we need a new new expression, I think. We have int, we have string, we have symbol, param. Yeah, we have a switch. Right, we could adjust the switch, for example, so that, sure, it has a condition, but then the cases, they don't just contain an egg body, but actually also parameters, basically. Yeah, basically parameters. Oh, you know what would be really elegant? Oh yes, currently the egg body is only contained in the switch, where we somehow need to add parameters in here for the cases. And it's used in the function, which also has parameters, which are, by the way, strings. And then you have an egg expression param that tells you, by the way, I'm referring to this string parameter. That's kind of, we can simplify that, I think. I think we can actually remove this expression and instead say that every body can have parameters, which is a slice of egg IDs. Okay, yeah, maybe we need the parameter thing. But not with a string, just, completely separate. Yeah. So then functions don't have this anymore. No. Yes, this also doesn't happen anymore. Oh wait, it gets even simpler. So this visible thing, the way we track which variables are visible, doesn't even need to have this it needs to have this distinction, but we never need to. Yes, it's a name binding local to a param, just that. Boom. Egg body compiler, egg body compiler. No. Yep, let's look at this. We have the egg body compiler, right? And this tracks the parent and params as well as expressions. So you can create a fun compiler, then create a body compiler, and in here params is similar to this right here. It's just an empty vector. Right, and then you can finish this, turn it into a body with params being body params to slice. Very similar to how this is done for expressions. And then you can either push a new expression or push a new parameter. compiled with nothing. This just returns you an egg ID. Right. So body parent expers dot push egg exper parent. We save an ID before that. Yeah, and then instead of pushing it to the expers, we push it to the parents. Nice. So then up here, yeah, the egg fun doesn't even need params. Yes. Oh, boom. Yeah, and here we don't say push, instead we say push parent. Nice. Yeah, egg doesn't have that. Don't need that. Nice. Right. When printing that, we don't do this. Yeah. We could just do this for bodies. You know, when writing the body, we basically, for each of the parameters, we also write that. Right, and then in the next stage, in the yogurt, we check that main body params len is 1. What? Yeah, when converting a fun to yogurt, what we really want to do is get the do we want to do? We want to get the fun parameters. Params is not a field on egg fun. Why not? Params is not a field. I mean, true, but do we need to? Oh yeah, we need to add them to this map somehow. Yeah, but this, you know, they don't even have a name. So up here in the yogurt fun, where are those used? Are they used? They're not even used. Oh, yeah, they are used down here. Okay, so this yogurt fun compiler doesn't even have params. That is, I mean, it is kind of weird that. Right, let's look at how the yogurt looks. A yogurt would probably have something very similar. Not have params here. Yeah. But instead in the body. And then down here, compiler.body, yeah. Oh, I see. And this is a yogurt body compiler or something like that. And that's actually where we want to do this. Yeah. Yeah. Here we want to say, hey, body push param or something like that with the egg ID. Yeah, with a, sorry, with a type, only with a type. Yeah, because the yogurt fun compiler, where is it defined? Where is it defined? Down here somewhere. Yeah. Doesn't need parameters. Because we never have to like look up parameters or something like that. Right, so there's a yogurt body compiler where we can push a yogurt expression. Okay, you know what, that's actually what we want to do. Yeah, that's what we want to do. Yep. Oh, hang on. We want to do something very similar. But instead push it to the parameters. And it only needs a type. Something like this, I think. Yeah, push param doesn't work because what's it called? Push param. Let's also call it that. Whoa. Yeah, expert is not in scope because it's yogurt expert param with this type. And that doesn't work because param is not an enum type. Because but it is. Oh, it's yogurt value. Right. Yeah, okay. And then compiler dot through the yogurt body compiler has the parent, but it also needs to maintain a list of the parameters that have been added. And similar to expressions, this initially is just an empty vector. Cool. Next, in here when we have a parameter, yeah, we push that to the compiler push param with that type. Now actually, what do we do for like references? Where are those? What? Like the egg? Ooh. Let's just see how this looks. Okay, so when finishing true, we need to do the same for parameters. And yeah, this doesn't make sense. It should be like this. True, totally true. And yeah, for the built-ins, we just push params like this. They are just some yogurt IDs. The fun doesn't even need this. It just contains a body with params. Yeah, actually, let's look at this. Wait, the params are also just yogurt IDs, right? Let's maybe do it like this. Yeah. This doesn't work because it already is a slice. Okay, sure. Oh, concise and readable. Yeah, same up here. Yeah, no. Basically move that into the body, the printing of the body. Okay. Unknown reference name B. True. Maybe before even testing this, let's just say yeah, let's just check that it's working in general. So something is not in the map. Where does that work? In lookup. To yogurt in the lookup. Yeah, basically says act to yogurt dot get. And that doesn't work because why doesn't that work? Okay, you know what? You should be able to just push an expression to a yogurt fun compiler and get back yogurt ID. This should just work automatically like this. So then in here we can just say dot parent dot push this thing, and that's the ID. Same here. Yeah, okay. We can get an ID, we can look up stuff. Why doesn't this work? Because this would have to be that. No, sorry, that. Okay, But this egg to yogurt, where do things get added to that? Oh, up here. We manually add them. After adding each expression, we then add the mapping. Okay. I don't quite like that. All of these just have a compiler.push, and that's all it does. Yeah, how about this returns a yogurt expression without adding it to the compiler. So it doesn't do this. It just creates yes, and then there should be like a compiler push expression, but it also needs an ID, an egg ID. And then this could just return a yogurt ID, but also add the mapping. So basically in here, we would say this expects an expression and an egg ID. Oh. Yeah, and it also adds a mapping. So that then down here, we can basically say push this parameter with an ID, an egg ID. Like this. Nice. And similarly in here. Nice. Yes, so then we can actually remove a yogurt fun compiler. Yeah, we convert the bodies to yogurt. But before that, yeah, let's say to yogurt on a body. So a body being an egg body. and it just, it takes a body compiler where it adds stuff, and then it returns a yogurt body, and it would basically just go over the parameters of the body, add all of them, and here, parent.type, I don't know. Type. Using that ID, and then add those to a list. And then go over the expressions. And what do we do, for example, with in the switch? Yeah, we just iterate over the expressions. We do that. And up here we do that as well. Yeah, let's just unify that. So for each egg ID, and body.expers do egg ID to yogurt. With a case compiler. What is that again? Yeah, no, just with the compiler. And then we say compiler.finish, and that returns a yogurt body. Well, first compile all of the parameters, then the body. Nice. Yeah, I mean that's pretty cool. Yeah, but also we don't really need this, to be honest. I mean, yeah, it doesn't hurt, I guess. All right, and we need to. Oh no, we push that to the compiler down here. Right. To yogurt on an egg ID. Where's that called? Yeah, no, not this. Yeah, up here, but we would replace that with just compiling the body. Sure, we have these. Okay, down here. But that would also be compile body. That's a function, that's built in. Yeah, I think. Yeah, no. Okay. We don't even use that anywhere else. So let's go even further. Let's say this down here is only called here. So let's inline that. Let's say compiler push. And you can see the parallels to this up here, to push param. Yeah. compiler.push with an egg ID. Oh yeah, like this. And that gets pushed to the params. But wait, the yogurt body compiler, doesn't that already have, it has params inside. Wait a minute. Yeah, okay. Yes, I think we don't even need a yogurt body compiler. Oh man, drinking sound. Yeah, I don't think we need a yogurt body compiler. I think we can just simplify this even further and just say this doesn't exist. We only have a yogurt fun compiler. Yes. Wait, but wait, down here we have an extra yogurt body builder. Let's unify that. Let's say that we have well, nope. Yes, we have a yogurt body compiler which doesn't have a parent. Yes, because there's not as much as a compiler as more like a yogurt. I don't like this. No, I don't like this. Okay, let's add a yogurt fun builder. This will just store expressions which are yogurt extras, so we don't need them here. Boom. Yes. And this will be very simple. Very, very simple. You can say I have a yogurt fun builder. You know, this is basically before we passed around like thousands of parameters down here, and we basically factored them out into this compiler struct, but it doesn't have a real coherent meaning. It's just whatever happened to whatever we happen to need down there. But this is more like a semantic thing, everything you need to build a yogurt fun. And yeah, so on a yogurt fun builder, which we're gonna call builder, yeah. choosing the right abstraction level is kind of really, really challenging in this case. Yeah, but this is a coherent thing. Just a yogurt fun builder, nothing more, nothing special. And it's completely separate from the yogurt fun compiler, which is more specialized, more higher level. Yeah, so let's just focus on the yogurt fun builder. You can push an expression. There is no mapping or something that it maintains. And this will be used both by for compiling functions that are in the egg, as well as built-in functions. They also use this. Okay, so you can push an expression. It returns the yogurt ID. That's beautiful. And the ID is just, you know, we create stuff, push something to the expressions. Yeah, that's basically it. Then you can also, like, you have push and you have get, and get on a builder and an ID just returns you the expression. Okay, you can do that. Yeah, this doesn't exist. Also, this doesn't exist. Or does it? This could potentially exist. You could say I have a builder and I push a parameter of this type. But there is no distinction between parameters and other stuff. So yeah, let's not do that. Let's not do that. Just this. Simple. Very, very simple. Yogurt fun builder. Quick constructor. Just as a constructor, push and get. Simple. Simple and coherent. And then down here, yeah, this doesn't exist. But instead we may add something like add mapping on a yogurt fun compiler with an egg ID and a yogurt ID, and it just says, I don't know, compiler egg to yogurt dot put something like this. Yeah, it doesn't even return anything. Great. Okay. Okay. Nice. Nice. You can add a mapping and you can look something up. Oops. And then finishing something, no, that doesn't even need to be like a data structure thing. This would just happen naturally in the code. So yeah, maybe let's move this further up here, even more further up here than there. Okay, so converting something to a yogurt. By the way, let's actually move this like up here, because this is like the fundamental stuff. Now you can associate a value and a type to an expression. You have this function builder. You have this function compiler. Okay. Now slowly we are talking. So converting an egg to a yogurt means we look for the main function and convert the main function for ints. Beautiful. It doesn't even need, yeah, it just needs that. Perfect. So converting a function to a yogurt only needs like the argument, the argument types, the name. Okay, sure. That's kind of weird, but I guess. Yeah, the egg and the yogurt. Sure. We get the signature, we get a compiler. Yeah, we create a compiler, we create a body. And here's where things get interesting. We don't do this. But instead, we say we create a builder, which is a yogurt fun builder. We can do that up here. I don't know. Maybe. Yeah. And then we just say compiler dot egg fun dot body, which is an egg body, dot to yogurt on the builder with a compiler. Builder and compiler. Great. And then this calls this right here, which means we go over each of the parameters, push that to this vector. We go over each of the bodies, push that to this right here. And yeah, this needs a builder, which is yogurt fun builder, and a compiler. Yeah, we just say builder dot push. Nice. Add that to this params thing. Beautiful, beautiful. And then we say we push that to the params. Yeah, that's basically it. And then for each of the expressions, we get the compiled expression and we say, hey, please push this thing. Nice. And then we need to map the IDs. So in here we need to say compiler dot add mapping from egg ID to yogurt ID. And the same down here. Yeah. So we have the expression, then we push that, getting the yogurt ID. Yes, builder. then we have this. Compiler.add mapping. Great. And also we need to keep the expressions. So vec of yogurt. Yes, very similar to what we do up there. And then instead of saying, let's finish this, we say we create a yogurt body that has params, that has expressions, and that has return value. Yeah, the return value is this. Whatever fun body returns, and we can get that. I'll compile a get thing. Yes. Right. This is a yogurt fun compiler. Beautiful. Just like this. And up here, where we convert a function to that, we just say convert the body, and all of this, we don't need this, to yogurt, and this will just be a body, which we then use down here. Wait. A yogurt fun. What does a yogurt fun have again? Extras. And a body. True. Express is builder.express.slice, and the body is the body. Like this. Damn. This is concise. So we compile a function by creating a function builder where we can push expression and just get yogurt IDs, and a compiler which maintains the mapping and also has access to like the egg fun and yogurt. Right, and this is not needed because this is in the fun in the builder. Okay. It's like fun body to yogurt. Yeah, I like that. Cool. The body is down here, has parameters and expressions, and this expression just it has a body. Wait, some wondering for the switch, for example. Shit. Yeah, I think the yogurt doesn't necessarily need to have the right well, let's leave it like this. Okay, so this is just a builder, which is the yogurt fun builder, and a compiler, which is the yogurt fun compiler. Right, and this just maps stuff. lookup works on a fun compiler. Egg fun is not in scope because that's the fun. So egg body needs, it needs, yeah, mutable things, references. Okay. Right, so for each of the parameters, it also needs the parent types, a slice of unit types. Yeah, basically assert that parent types .len equals .body.params.len. Cool. Yeah, so here we have the function with the args, right? And the args aren't even used right now. Well, okay, for the signature, not for anything else. So we should pass them down there. By the way, let's call them param types, just to be precise and correct. Yeah, this is cool. Yeah, let's inline that. True. There are no parents or anything. Just like that. Right, this is builder. Okay. Oh, we don't need that. We don't need to create a compiler and then do stuff. No. We can just say, build the body, please. Right? I mean, on a body, we can just say to yogurt with. Yeah. Switch case this. Yeah, this is a yogurt body. Oh wait, this is switch. So it's an egg switch, egg bodies, I think. And then we get that, and then we say, instead of doing all of this, let's just say body is case to yogurt. Yeah, the payload is for now, yeah, exactly that, an empty slice of yogurt tabs, but we should do something better. And then we have the builder and the compiler. So that we don't need these, we don't need this, just becomes simple. Wow. Very simple. Yeah, for call. Yeah, we get the receiver, check the definitions, and stuff. Cool. And in here we can just say returns is, well, you know, the body dot returns. Oh, no builder. What's builder? That doesn't work. Okay. Right, because it's yeah. So compiler dot look at this. That's more like it. Oh, right, but that's just okay. Never mind. Yeah. Okay. This is a lot cleaner than it was before. Like a lot cleaner. Okay, the switch is formatted in a very weird way because it's right here. Yeah. I mean, yes, we need to have this and then print the key, but then we don't do this, but instead just write the body, which takes care of printing a leading new line and parameters, if it has some. Oh yeah. And look, functions don't even have like named parameters or something like that. The plus function, taking a 2 and a 1, just accepts the yogurt IDs 0 and 1. And then here's the body. And here it calls, for example, 2 with the ID 0. So that's, it's just so much more consistent. Everything is so consistent. Oh yeah, using add for builtins is kind of weird here. But okay, I guess that's the way it is. So clean. This is super clean. Okay. Yeah, so the entire like the yogurt thing with the IDs is now refactored in such a neat way, honestly. Rather than, oh right, we haven't even simplified the thing down here for the builtins. Because for the builtins, you know, they don't need this. Well, I mean, they kind of do. They don't need this. Yeah. Okay, the parent is that you would find it. It can at least be simplified, you know. And you can push an expression, getting your good ID back by basically pushing stuff to the parent. Yeah, push expression that gives you an ID, and then you can push that ID to the body. Okay, sure. Yeah. Yeah, the body builder is just called body, because why not? Yeah, it has a parent, which is a reference to the fun builder. It has a body, which is an empty thing. Yeah, I don't know, something like that. Try to assign something to parent, because parent is supposed to be a reference to that. Then we have the parameters. Push stuff, sure. Built into yogurt. Yeah, okay. And the params. Alright, you don't even need these because you can already get them. Yeah, we don't need them because you can always get stuff from body builder. Cool. Cool. Yeah. Signature, build a function, add the function. What? No. Nice. Archetypes is not in scope. True. Because in here we just do args. Well, params. ID get back expression. Okay, so body get, no, sorry, body get parent get ID. Yeah, okay. Yeah, we can actually do that. Right. Yes. Cool. Very cool. Nice. Wait. Oops. Do parameters need to be added to the body? They don't really, right? Like this is cool, I think. Just has the parameter 0 and it's used and it starts with 1. That's fine. This is, oh, it's type info. Why does it do that? Takes a 0. Oh, I see. We have the params, but they don't need to be pushed to the body. No. They just need to be pushed to the body parent. Type info foo, yeah, accepts 0 and then it does stuff. Cool. Very cool. So, what do we do here? I think next, yeah, now we can actually look at, like, now technically bodies support parameters, but they are not used yet. So now we should be able to do that. So create something like this, bar B, and actually use that B. Yeah, so we have the toast, and we want to convert that to the egg, and that fails. Egg, we have a switch. Oh, that's just printing. Down here is the actual stuff. So if we have a switch, we compile the condition, sure. We have the cases, right. Then we snapshot them, we create an egg body compiler, I guess. And then we say, hey, case body, finish, flip. Yeah, this is kind of weird. Let's just turn that into this. And also for each of the parameters, so for we basically want to visible.define or something like that. Param.name. Param. Yeah, I think just param. A new egg expression. So case body push param of no, that's it. Push param, right. So this call doesn't compile define. Oh, this is an egg ID, but it needs a name binding. Yeah, it needs some name binding to local. Like this. Great. And it returns something. Beautiful. So let's look at what that does. Oh, body params, that doesn't match number of param types. Whoa. Where does that happen? Well, we call toYogurt on something, then we call toYogurt on a function, on a body, on an expression, on a body. Okay. I see. Yeah. And here we say body to egg. And the case body is a toast body, possibly. It's just a toast, like the toast.body variant. It's yeah, and then the toast it exists. Body params len. Oh, right. Oh, this is the yogurt. So the egg thing succeeded. Really? Let's see. Okay, where's the main function? Up here, main. Okay, so we call this. Oh no, a new line's missing. Right, so let's fix that as well. when printing an egg, what we do is we check, is it a function? And then we write the function body. Oh, it's a value, yeah. If it's a function, we just immediately write the body. And that actually seems fine to me, because the body should print its own new line after the parameters. So the body prints the parameters, but then it should print a new line. Okay. Let's have a look. Main function. Yes, we have a symbol foo. We have an int 3. We call foo3. We switch on that. If it's a foo, then we have an argument named for. Oh, nice. That's the payload. What? And then we create a 5, and it's a, and you know, stuff. If it's a bar, then we have a payload 7. Oh, that's beautiful. That is so beautiful. All right, so that doesn't get correctly converted into yogurt, which means let's have a look at the yogurt. Yeah, when converting a switch to yogurt, we go over the cases, over the variants that they can possibly exist. We get the corresponding case. We get a body. Oh, and look at this. We pass in an empty yogurt type of, but of course, here we also need to assert that the number of bindings matches the number of things in the variant. So for each of the condition variants, variant.key, yeah, we need to assert that variant.value, which is a slice of yogurt types, that this, the length of that matches the case params. Has okay. And then here we just have the variant of value. Boom. Oh, it's a, and then we have a foo with a for. Crazy. It's kind of sad that the type is not displayed here, but sure. But we can still find that out if we instead create a bar. No, we don't. We do. So we switch on this, and it can only be a bar with payload for, in which case we return the payload for, and that has the type 3. And that's true because here we create a bar, the tag bar, with the 3 is the payload. And here we unwrap that again. So we have the 3. What? Okay. Support enums with payloads. Yeah. Oh, what's the next step? And there were basically two things left. One is compiling to C, and the second one is error handling. Yeah, those are the two big things that we could do. I think compiling to C is more interesting. Okay. Let me adjust my desk because I've been sitting for too long. Okay. So, compiling to C. You know what? Let's actually draw things down. Okay. Well, so before we had this. This is the current state. We compile source code to, well, not ilt, it's called bacon. Got renamed. Yeah. And then toast, egg, and yogurt. And what we basically do now is convert the yogurt into something that's more higher level, which is C. So that we can then, compile C to machine code using GCC or whatever C compiler you have. Right. So I guess let's do that. Which means we kind of have to think about how do we want to represent values in C. If we have an enum, how do we map that to C? Also, you may notice that yogurt is lower level than C. And that's not, like, it's mainly different, so C has other features, but actually we only need a subset of the C features. We don't use all of the power of C. So even though C has, I don't know, you can nest expressions, we probably won't do that because we already have a flat series of instructions. Okay, so I guess we'll have to look at C. Yeah. But before we do that, I'm going to get something to drink. Okay. So before we had a separate file for each compiler stage. I think we'll do the same for C. Yeah, C is just C source code. It doesn't even have a tree or something anymore. It's basically just a big string. But I think I'll still add a struct for that. So this is, C source code, struct C, and that's just code. And then we have to C on yogurt, which returns C. And the way we'll do that is we have a string builder, and then in the end we call string builder.toString. Cool. Okay. So what we'll do now is, first of all, import that here. Compile that to C, and then is yogurt.toC, drag line C, and then we have the C code. And by the way, the C code will just print yeah, basically just the code, right? Yeah, that's it. I mean, the first thing is a generated file to edit by hand. Okay. Yeah, maybe let's think about how brainstorm. We'll see. In the end, we'll probably have a main function, which is always generated. This just has argc, argv, returns an int. Yeah, and then each function, if we look at the yogurt, we basically have functions where, like, for each signature, we have a different function. Here's the function plus with foo and bar. Here's the function plus with 2 and 1. And we basically want to compile each of those functions into a function, I think. So in the end, we really want to have a function plus 2 and 1. Like, we can't name a function plus in C. At least I think we can't. Yeah, so this returns something, and then it's called, I don't know, maybe something like this. Plus 2, 1. I don't know. Like, for example, you can imagine that each, or just plus 2, 1. Yeah. Yeah, something like this. 2 and 1. I don't know. We somehow need to mangle that signature into something that is valid in C. And then the parameters are just, well, they have the types 2 and 1, which means we somehow need type 2 and type 1. And then we can have the body in there. Yeah, this returns a 3, so something of type 3. Yeah, actually let me compile this down here. Okay. Well, the last expression becomes a return. Yeah. And this is a symbol content int. Okay, so maybe we first have to think about how we represent types. We have several possible types. These. No, those are values. These. So if we have a Comptime int, I think we can just turn that into something like this, a struct type 3. It doesn't even need to like contain any values, because everywhere where we use that type, like, you know, Comptime int doesn't even have any runtime information. Then we have a struct int, which, you know, we could just map to, is it like this? I'm not sure. Or this. Oh, type def, right? Type def. Oh, and there's an int 6014. And this is already like a standard int.har. Yeah. And here, like the low-level design decisions basically come into play. How do we want to represent ints? It's definitely a signed integer. I think we want to allow something like -5. But maybe we want to allow different integer bit widths, not just 64, but have like bytes, for example, that they can be more, that you can be explicit about. I want to represent this as a single byte, and then it's more efficient. I don't know. Maybe that's something worth thinking about. Okay, but we have type 3, type int, maybe. That would be these. Then we have type Comptime string. So type string, and then you know, the string content basically. It doesn't need any runtime information. Then we have enums. Whoa. So for example, let's say we have something like maybe 5. Okay, maybe int or none. Some int or none. This could be a type sum of int. And yeah, none. Maybe. And this basically enums need to have a tag to tell us which variant is active, and they need the payload. Ooh, so a tag could be an enum, but they have a global namespace. So yeah, this would basically mean you have to prefix all of them, like this. Like this, right? Yeah. Or we just save a byte. Nope. Or kind, or variant. Yeah. And then the compiler maintains that, you know, sum is 0, none is 1, something like that. And then we have a union. Yeah, a union with like, by the way, union, if you don't know, is like basically you can define multiple things in here, and they have the same memory. So if you write f, then you also overwrite the memory of t, and the other way around. And a union only has the size of the biggest thing inside. they also call it tag, because usually this is called a tag, tagged union, because you have a tag and then the payload. Yeah. This is, I like to call it as, and then have the different, variants in here, because then you can access this as if you're in a function and you have this, you can access it like the payload like this, because this is of type int and this is of type nothing, none. Yeah, type nothing. I don't know. Okay, I see. Yeah, and type nothing is just empty. Why? Oh, right. Oh, no. Because in C, the name of this type is not type nothing. No, the name of this is struct type nothing, which is just horrible. So you can do type def of this struct and then the name. Oh, how I love C. Look at this beautiful language. Oh god. Yeah. Nice. How's this? Oh no, it's variable declaration with this type. C is such a weird language. Okay, but this doesn't work because we need to have a type def of this struct as that. Okay, and then this works, and this is okay. Oh yeah, it's type int. The type gets inferred. That's nice. Okay, so yeah, Comptime string, got that. Just a normal string would be because like C doesn't have strings, so I think we'll have one type string with a data, which is just this, and length. Standard lib or something. Yeah. Okay, we have strings, we have enums, which are represented like this. Functions. I mean, they are only, they don't have any runtime information. Type fun, and then the signature. Yeah. And finally the never type, which is actually interesting. But I think we'll just have an empty struct. Because, I mean, sure, this struct will never be created, but that's fine. We just need to have some type to put there. Okay. So, okay, we have Comptime int. We have normal int. We have Comptime string. We have normal string. Yeah, this, we'll have to look at this. Well, we have enums, which is this entire thing. We have thumbs, and we have another. Okay. And then, yeah, then we need functions. And I think it makes sense to have something like this. So first we have all of the types that are needed, because you can only define things from top to bottom. So of course you have them up there, and then you have functions. So yeah, functions. We have concrete types. Type. One, two, three. Yeah, and this would be, the type would be type fun something 3. And that it's not initialized, so why is it formatted so weirdly? Wait. What? Yeah. Okay. What's going on here? We have a type. Wait. Yeah, 2 is this. Sure. Then we have something of type 3. Yeah, that's actually the expression 3. And that's the result of calling this with an argument. And calling means we have the signature right here. So we can just take the signature and call that with 0. Type info, yeah, and it's Comptime int as the result. The symbol Comptime int. It's basically an enum. Type Comptime int. Yeah, tag 0 is Comptime int, 1 doesn't exist, and yeah, something like this. Okay, yeah, we call that, sure, and then we switch. Okay, we switch. Right. How do we do that? We basically, we can just convert this to a normal switch. Even better, we can just say, let's first declare this thing, 6 of the type 3. Then we switch over whatever we want to switch about, over the kind of that Comptime int. And if it's 0, then we do stuff. What do? Well, we have the fun built-in add. Well, so we have a type from signature for Comptime, so we don't need to do anything. Basically, whenever it says Comptime in here, we don't need to initialize this type because it contains no runtime information. Okay, and then we have a type 3, which is the result of calling that, built-in add with 0 and 1. Like built-in add of 2 and 1. Yeah, and then that's the return, like the result of that switch case, which means, hang on, this is 5, which means that 6 equals 5. Okay, and then finally, we just return 6. Yeah, so this is what a function would basically compile to. Right, Comptime int has no, oh, right, it's tag. This is type of, of 0, of int, of 2. Yeah. Cool. Yeah, and basically we compile every single function into something like this. And then in here we call the main function, which will be like, call main of int with some number that we want. For example, with a number of arguments, why not? And then you could actually execute the program with different inputs, like different arguments. That's cool. That is super cool. Okay, I think there is still a lot we have to do to achieve something like this. Like, let's just start by writing the boilerplate. We always need these kind of things. Then we always have the types. And yes, there are some types that we need to compile, like int, or like, 1, 2, and 3, and so on. You know what, let's actually move this in here as well. Like this. Yeah. And then basically for type in used types, we basically want to switch on the type. And then if it's a Comptime int, we basically want to compile this to this. Okay, you know what? Regardless of what kind of type it is, we want to add a comment explaining that. So this. And then we have the builder this. And yes, this is not string interpolation, it's just that. type and then the integer. That's basically it. Yeah, if it's an int, well, then we want to compile this. Yes. If it's Comptime string, we want to do this. And yes, this, like all of this is not correct yet, but we'll get to that. Also an empty struct with Comptime string, then the string. And yeah, this is like totally unsafe. You can't have spaces. Like if you have spaces in there, something breaks. But we'll fix that later. Yeah, if it's a runtime string, then you know it's always just this. Type def struct. Actually, let's put it on one line because why not? Yeah, if it's an enum, well, this is where things get interesting, because then for each variant has payloads, which is a slice of payloads, which means that we basically want to first compile types for the payloads, like this nothing thing, or type int, you know, to do compile payload types. And then we want to have the actual struct. Oh. Yes. And let's actually continue afterwards. Okay. And then the function. So if it's a function, yes, fun. Perfect. For the never type, it's just this. Okay. Yeah, then we have all of the types. Next, all of the functions. What is this? Oh, it just wasn't, that was just an example. Yeah, and then we just compile a function. So first the return value, then the signature, and then the arguments. And found out params, do, and then, you know, we can do that later on. We'll just commenting all of this out. And then in the end, we compile the main function. Yeah, and that's it. Actually, let's replace these with to-dos and comment out this, and then, yeah, let's see if this works. Right, we already printed. Whoa. Whoa. Okay, yeah, so C, yeah, naming it type C is kind of C code. And that's, camel case is kind of, that's okay. C code, where the code is that. Yeah, use types don't exist, that's true. Yeah. True. Build type. Okay. Okay. True. Params is not a field. Right. Oh, down here. Yeah. Okay. Whoa. Okay. Yeah. This is a generated file. C. You know, let's actually print a new line before that. There's a generated file, do not edit by hand. Nice. And then, yeah, we need some new lines here. Oh yeah, and then all of the types. Wow, cool. And the functions. Whew. So I think what we need next is basically go over all of the types. Yeah, but basically collect all of the types. Yeah. Have some way of collect types on a yogurt. And that returns a slice of yogurt types. Nice. And then what then? Then we basically yeah, for each of the functions we go over the body, collect all of the types of the expressions and of the parameters and so on. Okay. Okay, so the yogurt fun has funs, which is a map from signature to something. So I think we would need to yogurt fun, and yogurt fun has expressions. Yeah, and on the bodies, they just contain IDs and other IDs and other IDs. So the expressions are the actually important thing. And the expressions, they have types. Those are the important things. So basically for expression in fun.value, which is the actual fun.expros, which are the expressions, do, and then we say the type is expression.type, and then we want to add this type to the slice. We should probably turn this into a set, I think. Yeah, you know what? For now, let's just add the types, because why not? Types is a vector of yogurt type, and then hang on, just types.push type, and that's it. That's easy. I was expecting, like, I don't know, recursive function calls or something, but nope. Okay, collect types in yogurt.collect types. It's not it is. Okay. Yeah, funds is not a field on yogurt, because on yogurt we only have true funds without an underscore. Okay, whoa. Okay, so we have some types. We definitely have some types in here. Crazy. Types. We have a type for the high string, because that's just, you know, an empty struct. Type Comptime string high. Crazy. Then Comptime string, the tag Comptime string becomes a struct with a tag with stuff. Right, so first I'm gonna add some new lines here. Yeah. Maybe add new lines before the type as well. Okay. Much more readable, I think. Okay, so we have types high. We have a Comptime string, which is a struct with a tag and stuff, but that's like nonsense. Then we have high again, we have world, we have a function. Nice. We have another Comptime string tag, another function, high world with a okay. Oh yeah, never. That's also cool. A lot of good stuff in here. Nice. Nice. Whoa. Okay. Cool. One difficulty is naming these types, because in C, and I mean in most languages, you can't have a space in the name of a type, or quotes, or several other things, or pipes or something. So we need to think about how do we name those C types so that they are valid names and they're unique to each type. So basically we need a function from yogurt type to an identifier that's unique for each type, like different for each type, but there's also a valid C string. And that's usually called mangling because you make the type basically more unreadable. You know, something like this is pretty readable, something like this is pretty readable as a type, but we need to convert it into something that's less readable, but you know, that at least works. So we want to be able to mangle a type, yogurt type, into a string. And here we can basically just switch over the type. If the type is, you know, int, yeah, we basically need to switch over all different types. If it's Comptime int, then we can just get the int and have that as the name. Oh, but then again, types can't start with an int. So maybe let's actually have like a recursive write mangle function that also takes a writer. But then also have a like top level mangle function that takes a type and just returns a string by creating a string builder. Adds type to that, followed by this. Yeah. So type always starts with type underscore, and then if it's just a Comptime int, it's directly the int. If it's a runtime int, it prints int, similarly for strings. A Comptime string Comptime string underscore and then for each character in the string we can basically check if it's a letter, then then we just write it into the thingy. Else we write I don't know, underscore, and then chart it to int as a hex thing. Yeah, and maybe then another underscore. Okay, if it's an enum, then we basically want to go over all of the variants. And we want to print the variant key. And then in here, we want to write the payloads. So for arg in variant dot value. Oh, now we call ourselves recursively with that argument. Nice. Yeah, and at the beginning, let's just write enum of and then end, just because I'm not entirely sure that it's unambiguous. Okay, for a function, we just write fun underscore, well, and then something very similar to what we did here. So I think it makes sense to be able to mangle a string. Yeah, and that's just this. And here this is just writer.mangle string, while in here it's writer.mangle signature. That's still okay. Yeah, never just prints never. But then we can have the mangled name, and that's just type.mangle, which is a weirdly named string. But then we can use that here. Instead of these ad hoc definitions. Right, to int doesn't work on char because a char contains a byte. We can turn that byte into an int, and then oh yeah, signature is just a string. That's even simpler. Whoa. So we have the type enum of Comptime int of end. And this is not really readable. It just tells us that this is an enum with multiple variants. So one variant is Comptime int, and then here are the arguments. There aren't any. And that are all of the variants of the enum. So this like off is basically like an opening parenthesis or something, and end like a closing parenthesis. Here we have the type 2, type enum of end. What? Oh right, the enum symbol. Oh, okay, yeah. I guess that kind of makes sense. Oh, but this, like, types are going to get so big. Let's actually make them a little bit more readable by, and here we can like check if variance, if variant.value is not empty, only then do we write this off thingy. Yeah, and here if variance.size, yeah, is not 1, only then do we print enum of and end. Yeah, okay, so something like an enum is just type enum. that's better. And Comptime int is just type Comptime int. So here we have type bar, here we have type foo, type fun, and you can see that 2b, that's basically the hexadecimal encoding of a plus. Same here, 20 is a space, and apparently this is a comma, and so on. So, you know, those are valid type names. Yes, type bar of 3, and that's reasonably concise, I think. And that's an interesting type name. Right. Okay, but we have these types. We should turn this into a set or something like that. Ooh, yeah, let's just try to do that and see where it fails. Oh, I think it's put or insert or something. It's put. True, we can't hash yogurt types, so we should implement that. Yeah, equals and hash. So equal yogurt type b, yogurt type returns a yogurt type, sorry, returns a bool, and okay. Yeah, this is kind of complicated. Okay, so we switch over the yogurt type. Of A. And yeah, basically for each case we check, hey, payload W, I don't know. B, is that also this? I don't know, if B is flim B, actually let's replace the V with A, then A equals B, else false, something along those lines. Yeah, okay, hash also needs to exist. So a yogurt type and B yogurt type. Oh, sorry, no problem. It takes a hasher and a single type, and that's it. And similar to this, it just switches over the type, and depending on what it is, it does different things. Because it just calls hasher.hash of the payload. Doesn't work. Hasher, hash nothing. Well, yes, will. I don't know. Put anything in there. Yeah, similar here. We should also add like a hash thing for which variant it is. You know, just like this. That's actually getting kind of readable. Yeah. For these, they don't have anything more to hash. This has a string. This has an int. Yeah. Okay. And that's also true. Okay. You can't hash a matrix. A map. Apparently. For some reason. Okay, you know what, I'm actually fine with that. Let's just have an imperfect hash in that case. Okay. Okay, so we have a set, right? 1, 2, Comptime string, Comptime int, never, foo, bar, enum, builtin add, bar 3, hi. Oh, there we have 2 already. No, only 1 and 3. And then 2, okay. So it seems like every type only exists once, which is perfect, which is exactly what we want. Okay, so we have types. We have lowered types to C types. Next, well, first of all, let's simplify this a bit. Like, I know we can. There's so much unneeded space in here. Actually, that's something that I don't like about like Rust or something. That is just so not even necessarily verbose. I mean, yeah, it kind of is, but that you have so much like wasted vertical space. Sure, this is dense code, but it's not more difficult to read just because it's on a single line, you know. You can even have more, like you can highlight the similarities. You can't do that if there's like 20 lines just for, you know, closing brace on an extra line and stuff like that. I like, you know, like concise code is really nice, and you can even, like, it gets easier to read just by being more concise. That's amazing. Yeah, similarly with the hash thing. I mean, you can really see the differences here. I mean, yeah, we should probably have a, I don't know, enum to byte or something, so we can factor this out of the switch, but still, you can really see the parallel structures between all the variants. That's not possible if you write everything below each other. Right, okay. You know what, let's do the same. Here, let's just clean it up. Yeah. Cool. Very, very cool. Mm-hmm. Okay. Ooh. Yeah, I think I'm going to take a walk, just so that I got outside today. Here we've mangled the types. Next, we should mangle the functions. Yeah, I am gonna do that today, but I need to move from, like, a bit. Yeah, okay. Yeah, Okay, I guess that's it for right now. See you there. Well, okay, I didn't program yesterday, so yeah, it's another day. But the only thing I'm gonna do is compile to C, and that's it. All right, so yeah, we already lowered the types, at least somewhat. Right, and what's remaining is lowering functions. So let's try to do that. Yeah. I'll share my screen. Here is the loop around functions. And basically we want to print stuff. So I think fun has a return type inside. Maybe not. Alright, fun.value is the actual function, which has a return, which does not have a return type. It just has a body dot returns, and you can do value. Can you do this? Nope, you can't. Can you do this? Yes. Okay, so this is the expression and we want to print the type. Let's actually return type is this. And then we printed the return type and the function signature, which is actually just the key, right? Mangled. This does not work because, right, you can't just mangle a string, you have to, let's actually change that. So mangle of some string is another string, and it's similar to mangling types, in that you just take the string, well, you create a string builder, you mangle the string, that's it. Okay, so this should work. Oh, it's yogurt signature, of course it is. Which has a string inside, maybe? Yes. Because a yogurt signature is basically already stringified. Then we are iterating over the yogurt body. Well, no, the yogurt body has, oh, yeah, body dot. Yeah, this is, we need something recursive because we want to, you know, convert the body to C, and then if there's a switch with another body inside, we also want to turn that into C code. So basically, let's create a fun to C, but instead of like this one taking a yogurt, we will take a body, which is a yogurt body, right? That exists, and returns C code. The way it does that is, well, similar to this. Creates a string builder. It returns this. Okay. So here we will just assume that the parameters are already in scope. Alright. Yeah, we still need to do that here. So body.params, something like this. Yeah. Actually, let's write the names, because why not? Yes. Fun dot. Oh wait, and these are like the IDs, right? So basically, fun dot value dot get. You know what? Let's get fun dot key and fun dot value, so that we don't have to write fun dot value each and every time. Yes. So much better. Okay, and then from the fun we get the param, which gives us an expression. We get the type. We print the type. And then a space. And then the name of the parameter, which will just be param actually. You know, that's an ID, so it will be underscore something, hopefully. Yeah. And then comma. Does C allow trailing commas? I'm not even sure. Like, can you do this? Nope, you can't. Well, gotta do the old first thing. So, yeah. Okay, so now we have comma separated parameters. Nice. And now we want to write the body, which is just fun.body.toC. Oh, you know what? This could actually be a generic overwriter. Oh, I love that. Okay, so we want to write the fun body, which means we have a body, which is the yogurt body, and a writer, and we want to iterate over the body. So for id in body.express, body.body, I don't know. Alright, this doesn't need to return anything because it adds things on the writer. Yeah, and for now we'll just, I don't know, just declare stuff like this. So get the expression from the fun, right? Yeah, so we do need a fun, here a fun. Yeah, expression is fun.get ID, and then on the writer we basically write the type and then the ID. And yeah, we will probably have to turn those into, I don't know, some stuff. Right, and then based on, you know, based on export do stuff. The actual value of the expression. Right, I don't have a terminal open, so let's fix that. Big. Oh, that's the maximum size. Interesting. Yeah, breakfast. And basically if there's enough space, then it prints all of these mono things on the same line. I'm just gonna zoom out one time. Yes. Better. Okay, yeah, so this doesn't work because it also needs a function. Like this. Nice. Okay, okay, I can work with that. Whoa, what? Okay, so there's definitely something going on. Let me put that in full screen. So we have the header, we have some files. Yeah, and types, some of them with constants, some with stuff. Alright, yeah, I need to fix the enums, sure. Oh, and these are functions, right? No, they're types. Wait, but here? Oh, right. Functions are also types. That makes sense, I think. is definitely a, oh yeah, here, functions. Oh, that's kind of easy to miss. Let's maybe add a new line here, and let's add 2 new lines here. Okay, so this is a function that accepts hi. Yeah, that's the type. That kind of makes sense. Because those should also be mangled. Sure. And then we have param. What's going on here? Right, so we have the parameters. Oh, right. So we also need to print a closing parenthesis, then an opening brace, and then the body, and then finally the end of the function. Yeah. 2 new lines, because why not? Yes, that looks a lot more like code. Okay. Nice, here are functions. For example, there's this function, type info of hi. It basically just, accepts a type Comptime string hi, and then it it creates a string So the question is, what do we do with the return value? It creates a string that's actually like valid code. By the way, annotation is also something we may want to write. Yeah. So first print some annotation, and then for C, I think it's common to use for, annotation of 4. Oh no. Right. We need more. We need to tell it how much indentation it needs. Okay. Whoa. That looks so much cleaner. Okay, so we have a Comptime string, and after we've lowered the body, we basically want to return the whatever the body evaluates to. So fun dot, or rather b dot, yes, return, and then what the body evaluates to. So fun dot body dot returns, and semicolon, because of course. Whoa, this looks amazing. So yeah, it accepts a type 2 and returns a Comptime int. Oh, this doesn't look mangled, I think. Yeah, return type dot mangle. Still need to do that. Is this mangled? Comptime int. No, of course it's not. Okay, Also add is not a valid identifier in C, I think. So, also need to mangle the ID. Same for the parameters. Yeah, and of course we need to support mangling IDs. So mangling an ID, which is the yogurt ID, results in a string, which is just ID dot or underscore ID dot int. Something like this. Okay, yeah, so this is, you know, it uses underscores. The return is still using an add because it's not mangled. Sure. Okay. Let's see. I mean, this is already pretty cool. So we have a function, type of high. It accepts a Comptime string high, and it then creates a variable of the type Comptime string, which is, you know, totally just a Comptime value, so it doesn't need any initialization. And then it returns that. Indeed it does. This function is basically correct. Next we have the function, what's going on? Oh, so this is the return type, hi world. Oh no. Oh, I see. This is like a plus. Right. So this adds hi, the string hi, to the string world, and accepts a Comptime string hi and a Comptime string comma space world exclamation point. Sure. It has some type info which is not initialized, which is, well, but basically this also works. Yeah. Here's a function built-in crash and a never type, which is never instantiated. Okay, so we basically need to lower the expressions. We just create, like we declare that this ID exists, and then we basically want to switch on the expression value. So let's look at what kind of expressions we have. We have these expressions. So parameter is unreachable because parameter expressions never occur in a body. They are only used by, you know, functions or body as body parameters. Okay, so if something is Comptime, we don't need to do anything at runtime. If we have a switch, well, this is basically the most complicated thing, possibly. If we have a tag, we also need to do stuff. Let's just write stuff, actually, to do initialize tag. Beautiful. To do switch. If there's a call, to do call. If there's an instruction. Okay. Whoa, this is pretty cool. Let's just look at the main function. So we create a bar and a 3, and then we want to create a tag, which is bar of 3. And then we need to initialize that tag. Yeah. Cool. Very cool. Okay, yeah, then we need to perform a switch and so on. But first let's initialize tags. Sure. I think actually the easiest thing would probably be to call a function. So let's first write some annotation and then write, you know, id.mangle equals the result of the call. So basically call the signature. Does that exist? No, it does not. Call that fun. Call. Oh, right. The receiver of the call is yogurt call has a receiver which is just yogurt ID. True. Receiver, that's yogurt ID, and then we get the corresponding expression. So fun.get of that. That for now has to be a Comptime. You know, the type of that has to be a fun. So type.fun. Let's actually factor this out. You can only call funs. Yeah. And we call that fun with some arguments. So basically we go over all of the arguments and call that args. That does exist, right? Yes, that's a slice of yogurt IDs. We just print the IDs. So again, okay, so we print the IDs in a comma separated way. arg.mangle. Great. And then closing parenthesis and semicolon and a new line. So now calls should work. Whoa, and look at this. Crazy. So here, for example, we call the plus function with foo and bar. Right, but of course the signature also needs to be mangled. So yeah, it's like that. Cool. Yeah, this doesn't actually, like, the name of the function is not plus, but rather it's plus of foo and bar. So this is not the signature. I thought that this would be the function signature. Well, okay, but let's first do the other stuff, switch and tags. So actually let's do switch first. I mean, well, both of these basically rely on correct enum implementations. Yeah, you know what, let's actually take all of this and put that in here for now, and let's just have something very, very simple here. For example, I don't know, comparing numbers. No formatting, no stuff. Just that. Yeah. So let's basically check what is, compare. We call this less. So we check less, is a less than 5? If true, we return a, small a. If it's false, then we print big A. I think that's reasonable. Okay. Expected expression. I don't know why that's happening. Does this work? It does. Strange. Alright, less is not a valid... we'll do that later. Yeah, but we only have plus, minus, star, and slash as supported characters inside of names. So less than is not a valid name. Ooh, yeah, we'll lift some of those restrictions soon. Right, but this is like a smaller example. And here, for example, we have a boolean, basically, which is true or false. So what we need is, first of all, have a tag and some way of, fixing this. Right, so when compiling a type up here, from enum we basically need to, well, this is actually correct. We have a tag, and this is not correct, because in enum has variants, and so for each variant, we basically want to print the variants. And then we have a union, and then for each variant, we basically print the variant type. Arguments, what they call it, a payload or something. Oh, like it's a map entry. Just value, which is the slice. Yeah. True. Basically do that instead of this. Okay, so yeah, this doesn't work because basically we need to think about how we represent those variables. If we have a, I don't know, some int, some int or none, if that's our type. We basically want to create an enum that looks like this. With a tag that either says some or none. And then this should be an int and this a nothing. Does that make sense? Well, the question is, what if it has multiple? What if we have this? We probably don't want to type int or something, because we don't have tuple types or something like that. We can instead just directly have a struct in here. And then for the none, this would just be an empty struct. That's actually cool. So struct with basically the arguments. So yeah, something like this. Oh, that's that's fine. Yeah. Okay, sure. So we write down struct and then an opening parenthesis. And then at some point we write a closing parenthesis. Yeah, and then for each arg invariant of value, we print that. So again, the type. Oh, and the index. So let's see what happens. Okay, so we have true or false. It has a tag. Indeed, and for the true variant, it doesn't have any payloads. The false variant doesn't have any payloads. So then here it has a union of true and false. Yeah, and they don't have any payloads. That seems correct. Yeah, let's adjust the annotation to be coherent. Okay. Yeah. This looks cool, actually. Very, very nice. Yeah, and for a false, for example, we have a tag, but sure, we don't actually need that from an information theoretical perspective, but we can optimize these later on. By the way, these are not there are ways to build way more efficient structs. For example, put the tag at the end because this is unaligned. Currently, if you have a struct with a tag and an int, for example, well, ints are usually aligned to, I think, 4 bytes in C, 32-bit integers. And that means that you basically have a tag of 1 byte, then 3 bytes padding, and then an integer. So yeah, the memory layouts and everything is not optimal. But that's not the focus right now. The focus is getting this to work in the first place. Cool, this looks fine. Also, the tag will basically be the order of these things. Because yeah, it's not like you don't have guarantees about the order, but at least it's deterministic. So yeah, less or equal or greater seems, or is it? I'll have to investigate it. I'll just assume it's yeah, I'll assume it's deterministic, and then if not, something will blow up. Right, so we have these. We want to implement a switch. What's a switch? Well, a switch basically becomes a C switch. So we write indentation. Then we write switch based on the condition, which will just be ID. Then we print an opening brace, and then at some point, a closing brace. Cool. Cool. And we already have declared basically the result of the switch. So the only thing we still need to do is for each switch case we basically want to print indentation and then case we need the type that we switched over, so the condition. Switch.condition fun.get of switch.condition and the type of that. Correct. Right, so then we basically go over the type. We're just guaranteed to be an enum type. Right, so we have the variance, and then this will be a map. This will be an iterator over the keys. This will be a map. This will be an iterator over the keys. And then we basically want to find the current case. True, but there are functions named that. Are there not? Defin. Oh, there's a typo. Well. Oh, so apparently this doesn't work. That's a map entry, so if the key of that is our case, then we set the index to the enumerated index. Okay, so then this doesn't work because we compare string and a map entry. This is also a map entry, true. Case and then the index, cool. And now we basically want to write the body. So something very similar to this, except with indentation +2. Cool. Whoa, that takes a long time. That doesn't seem right. Why doesn't that work? Why doesn't that work? Strange. Wait, but if I remove this, then it works. It does. Crazy. Okay, so let's just print let's not print the cases for now. Okay, that also works. Yeah, let's just print case 0. Yeah, so this is a switch over the enum of true and false. Yes, we can also add this annotation. Cool, cool, cool. This works. We check if type int is less than 5. And then we switch on that result, which is either, you know, it's true or false. Then we find the correct index. Nice. So this basically just goes over this map of map entries, and it sees, well, true is 0 and false is at position 1. Great. And now we want to write down the... Oh. Okay. Yeah, we don't want to write down recursively the function body. Nice. Oh, that's actually super cool. So we have a Comptime string small, and we can have a Comptime string big. Oh, and now we basically want to assign them to this string result of the switch that was declared up here. So for each body, after we lowered this, we then want to say, hey, let's take the ID and let's assign, well, case dot value, which is the body, dot returns dot mango. And yes, this will be invalid code in C. Yeah, because you can't just assign a Comptime string small to a variable of the type string or big to that string. So we need to, you know, cast this or convert this somehow. Okay, but apart from that, this looks super cool. Cool. So next, instructions. Or tags, that would also work. You know what, let's first look at tags. Okay, now to do that we would have a, it would help to have a program that actually uses tags. Structure is not an enum, right? Because instruction has instruction inside, right? I hate this, but okay. Yeah, we just basically say, hey, we take this ID and that should be the result of adding those other numbers together. So instruction.args get 0 dot mango plus we have add, we have subtract, which converts to a minus sign. We have null, which gets converted to a star. And div, which becomes a slash. We also have compare, which is a bit more complicated. So basically we need to compare numbers. Yeah, so basically if you know what? Okay. Yeah, if args get 0.mangle, if that's less than args get 1.mangle, and by the way, down here these should also all use the second argument. Yeah, if that's the case, then we basically want to assign less, which is 0, I think, I hope. Yeah. If they are equal, we want to assign 1, and if it's greater, then we want to assign 2. And these numbers may not be correct, but we'll fix them later. Right, if we crash, then we basically want to, if for anything, we know that the first argument is a string, so yeah, we just print that like this. Yes is yes or no. Nice. And then we can actually exit. You know what, let's do stuff like this. Yeah. Okay. And yeah, this needs indentation and all that stuff, but yeah, let's add that. So before an instruction we print indentation, and then for the multi-line ones we also need to add indentation before the instructions, and similarly here. Okay, nice. And then we don't print this. Did we miss a built-in? Oh yes, we did. Concat. Okay, so concat is actually, you know what, we just tried it to do. Yeah, new lines. Make things more beautiful. Similarly here, semicolons and new lines because we are in C. Cool, cool, cool. Whoa. Oh, look at this. We compare int to a 5. And the way we do that is we check is the int smaller than a 5. Then this enum will be set to 0. Nope, the enum tag will be set to 0. So yeah, and here we need to say that. Right, and then we just return. That's cool. Okay, so we can't compare ints and 5s, for example. And we can't just assign compile time string small to a variable of type string. So we need to upcast values, basically make the type less precise. The type 5 is more precise than the type int, and the type compile string small is more precise than the type string. But in some cases where we have like branches or stuff, we need to take the more generic type. Yeah, whenever we have branches or when we have instructions that operate on like concrete values. And that basically means we need to convert the more specific type, the Comptime value, into the more generic runtime value type. Because at some point we need to actually like create a 5 in memory or somewhere in some register in order to be able to compare this value to 5. We have to create the 5 somewhere. So I think the most elegant way would be to add a new yogurt instruction actually, because you know in the yogurt we already do the type checking in everything, and there we basically see that we assign a type Comptime string to a variable of type string. So that's like pretty easy to add a cast instruction here that first converts this Comptime string into a string, and here converts this 5 to an int. Right, so let's do that. Let's do that. Let's do just that. Cool. Yeah, let's look at the yogurt, and we have a new cast instruction, a cast value. So hang on, param Comptime switch tag call instruction, yeah, just here, a cast, which takes a yogurt ID, and the type to which this ID is casted is determined by the yogurt type of that surrounding expression. So the value will be cast and the type will be the cast that it should be casted to. Yeah, we need to be able to print that. I know. Case cast ID cast that ID. Cool. And then we need to insert that at some points. So we saw 2 places where we need to cast values. One was when joining branches of switches, and the other was when invoking instructions, because the instructions always need like specific runtime types. Let's first implement this for switches, which is right here. So basically we have our cases, we have the case types, and then for each variant we, cases is a map to yogurt body. Yeah, basically we need to add a cast instruction after into the bodies. Right here we join the types. We've lowered all of the types, and we've found out like the common type of the switch. And basically for each case, if the case if the corresponding case type is what was it called? Builder get case dot returns that type, and if that case type is not the same as the common type. Let's actually call this common type to be more descriptive. That's not the same as the common type. Then we need to insert a cast from, you know, the case type to the common type. And actually let's just print that. True. If needs a then. Oh, right. Yeah, the cases are map entries and these are the bodies. Okay. Yeah, when converting this to C, things get more interesting. We basically need a new branch here. So if a cast happens, to do handle cast. Okay, so I hope that up here it printed some debug things. Yes. Yes. So here we have a true, and we basically need to cast that true to true or false. We have a false, and we need to cast that to this. And here we have a string like small a, and we do cast that to a string, and so on. Yeah. Okay. How do we do that? Like, the problem is that this just calls, you know, it lowers the bodies independently. No. Here. It lowers the bodies, but then it converts the entire body to a yogurt. And once that's complete, you know, this returns a finished yogurt body. That's basically what we do up here. You know, we have a vector of params, a vector of expressions, and then we turn those into slices and do all that crazy stuff. So actually adding a new expression at the end is kind of difficult. Yeah, maybe it makes sense to pass that here. Basically oh no, we can't pass the expected type here because we don't know the type yet. We first need to actually convert all of those things to bodies, then find out the common type, and then later on add cast expressions to those bodies where the type doesn't match the common type. Well, that's... Ooh. How do we do that? I mean, yeah, we could just, yeah, basically get the content of the body. Yeah, let's do that. So we basically destructure this body and replace it with another one. Yeah. So this is a body, and then old body is this. New expros, sure, is a vec of yogurt IDs. And then for each expression in old body expros, we basically add it to the new expros. And then now we also add a cast expression, which has the yogurt value cast and the type common type. So we want to cast this specific expression to a common type. Yeah, and this needs the return thing, which is old body dot returns, and this returns a new ID of what the body now returns. Yeah. Oh, like updating these while we're iterating over them. That's seems cursed, but it should work. In this specific case, it should actually work because we only overwrite existing entries. We don't add new map entries. Still cursed, but well. Right, so case.key, we add a new yogurt body with, you know, params being old body params, expros being new expros per slice, and returns being the new returns, like this. Yeah, this call doesn't work because this is an expression, and we need to add that on the builder. So builder.push, was it push? I'm not sure. Apparently. Try to assign nothing. Oh no. New returns is this. New returns. Yeah. Yeah, let's actually add some new lines here. Maybe some high-level comments. Lower all that are used by the condition type. Common type of all branches. That cast expressions where necessary. Right, and then in the end we return a switch. Like this is definitely cursed, but ooh, look at this. Okay, okay. Nice. So here we have a switch, and in one branch we have something of the type small a, and we cast that Comptime string to a string. And similarly here with the big A and with these. So we have a symbol true, and we cast it to true or false. Beautiful. Okay, so yeah, handle cast, we need to do that. But also in the compare instruction, we need to add casts, because the compare instruction always accepts two ints. It can't be that one is an int and the other is a 5. So down here, when lowering the built-ins, we have, for example, for add, we check if they are both Comptime ints, then we just, you know, we know the Comptime int, and we don't even need to push an instruction. Otherwise, we basically want to add, you know, we want to turn this into an int and cast that if necessary. a type dot to int cast to int maybe with a builder, and this is this is a type. Yeah, let's maybe, I mean, a type and b type is not even shorter than just writing a and b like this. Okay, so we have a and b. Okay, you know what, let's do it like this. Okay. Okay, we have a and b, and then builder get a dot type, builder get b dot type, and sure, let's do this. Yes, otherwise we say a is a dot cast to int on the builder. Cast to int will be defined down here, and it's very similar to the isInty. Cast to int id on a builder, which is a yogurt body builder, immutable, and it returns a maybe. So it basically switches on the builder.get id.type. So the type of the expression with that ID. If it's an int, then we are fine. We don't need to cast it to an int. It's already in it, so we can just return the ID that this thing gave us. Otherwise, if it's a Comptime int, well then we actually need to push something to the builder. So builder.push yogurt value.cast to the type yogurt type int. Yeah, please cast this ID to this int, and that returns a new ID. Yeah, and for all other types we return none, because those can't be casted to an int. And we'll do something very similar to strings. Cast to string ID get type. If it's a string, we're fine. If it's Comptime string, we cast that to a string. Yes. And then we don't need these, but instead we just say cast to int or panic. Then we also do the same with b. Nice. Oh, yeah, and then the params are not just this slice. No, they are actually a and b, because they might be different. We might have added some cast expressions. Great. I like that. Yeah, let's do something very similar here. So yeah, I think the first part is basically the same. Yeah, if both of them are ints, then we'll just do this. We get the correct symbol, and we push a Comptime symbol. Yeah, otherwise we want to convert them to int. Here. Yeah, and then we have compare with those args. Beautiful. Finally, when concatenating things, we have again something very similar, where we just get a and b, and we check if builder.get of this .type is this. Yeah, do the same for b. And we push a Comptime thing. Great. otherwise we cast them to strings. And then we push a yogurt instruction with those as parameters. Great. So yeah, this makes sense. Yeah, and we don't need to adjust that. Okay, for the crash, we do something very similar again. So basically we say the message is params.get 0.cast to string. The builder, using the builder, and then the arg is the message. Yeah, or panic crash only accepts string messages. Let's see what happens. Whoa, look at this. When comparing the int 0 to the 5, 1, we first cast this into an int. And then we have the compare instruction, which compares this runtime int to this other thing which has now been cast to a runtime int. Beautiful. Wow. Okay, so in converting these to C, I mean, the only casts that are allowed are basically converting Comptime ints to ints, converting Comptime strings to strings, or converting enums to other enums that are a subset, no, superset of the enum before. Boo. Okay. Sure. So basically we want to look at the type that we want to cast to. Which is this right here, expl.type. If we want to cast to an int or a string or an enum, yeah. Okay. Yeah, so when we cast to an int, we basically know that this is a Comptime int. You know, so the only thing we need to do is, what was the definition of ints again? I want to see a run where, yeah, here we have C code. And yeah, this is the int type. Oh, I see. So yeah, an int is just int64t. So we can just say this equals, you know, whatever the Comptime int. So cast dot, wait, that's an ID. Yeah, now we want to get that ID like this. And we want to get the type. We know that's a Comptime int, so we can unwrap that. And that gives us the int. So that in the C code there will be something like something, you know, ID equals 5, because the type of this was Comptime int, and now we basically create a runtime 5 from that. Okay, for strings it will be pretty similar, I think. So strings are, yeah, string is, okay, it's a struct with data and len. Right. and len. Yeah, I think we'll just create two expressions where we set the data and the len. And let's maybe first unwrap the string, the Comptime string. You know what, that's actually readable. Yeah, it's fine. It's fine like this. Okay, so data is just string dot string debug. I think that's actually fine. It prints double quotes around the string. It prints new line as \n. I think that's a fine way to do this. Yeah. And this will just be string.len. Okay, for enums we have a to-do. Cast enums. Yeah. Okay. Whoa, look at this. We have a switch, and we want to get a string out of that switch. And here we have a compile time string small. But then we want to cast that. So first, crazy. First we create a string. We set the data and len, like, you know, this is a runtime string. And then we assign that to the switch result, basically. Same with a big string. Okay. Okay. Noise. Yeah. I should print indentation. So here and here, I think. Beautiful. Yeah. Just create runtime strings from Comptime strings. Oh, and similar with the int. Here we have a type 5, and we want to convert that to a runtime int. So yeah, we just create a runtime int and set this to 5, like the actual value 5. And then we can compare this, you know, this other runtime int to this runtime 5. Oh, that's amazing. That's super cool. Okay, we support casting. Right, casting enums. So, yeah, we need to do that. How do we do that? We basically need to, oh wait, we need to switch on the enums, right? Yeah. Yeah, because you may have an enum with, like, you know, variants A, B, C, D, and another enum with A and C, for example. So you can't, there's not guaranteed to be a one-to-one mapping between, like, a subset of the tag IDs that we choose. Yeah, we basically need to switch on the existing enum and then upcast that. Oh, damn. This is not at all complicated. Okay. Yeah, let's do that. So, we basically want to switch on the thing that's being cast. For each case, for each type, I don't know, each All right, we need to get for each something in fun.get cast gives and .type gives us the type of the enum. That's an enum, we know that, so we can unwrap that. Yeah, so this will be a map of from like enum variants to the payload, and we can iterate over that. And for each variant, we want to print case the index of that variant. So basically, we want to iter, but enumerate it over this. Yeah, and then if it's this variant, then we basically need to look in the target type. So yeah, the expression type, which is guaranteed to be an enum. Yeah, target variants. But that will be more complicated. It would actually be pretty similar to how we do a switch up here. Yeah, so we have a target index, and for all of the target variants, we set the target index and we break, yeah, and we assign this to the ID. Cool, I think. Yeah, if that ID, so if that key matches the variant key. Oh, sorry, variant.item, which is the map entry.key. Not at all complicated. Okay, so something happens here. Yeah, we have an enum with only one variant called true. So then when we want to assign that to the enum of true and false, we switch over the true and basically see, hey, we need to switch over its tag. Yeah. Yeah, we switch over its tag. And then if this is, yeah, I mean, true can only have one possible tag, which is 0, which is the index of the true symbol. Then we set the tag of this thing also to 0, because true is also 0 in this at 0 position in here. Here's different. Here we have a false, and in the enum false, well, false has index 0, but in the enum containing true and false, false has index 1. So here when we switch over the tag of the false, we basically see, okay, this is a 0, so we set this tag to 1, because here false is at index 1. Okay, yeah, let's just add some new lines and indentation and stuff to make this beautiful. I mean, this entire code in this file is not beautiful. It's like very hacky C code, but that's fine, because I mean the C backend at the end is just temporary until we like figure out the language and create something, something better. But so I don't worry about too much, too much code being hacky. Yep. And I mean the concepts of like, upcasting values and everything, that's still very relevant to other backends when we choose to I don't know, compile to machine code or something. Right, so here we just write the cases. Yeah, like this. Maybe let's add a new line here. Okay, this still goes over the line limit. You know, I like languages that have an if then and a for do, because no matter how complicated this thing is, you never have something like, you know, where you have this. That's just ugly. You always have an introducing keyword on this line. Also for an if, you can have an if with a huge condition that spans multiple lines, and then just have a then on the same indentation. That's just elegant. Okay, so, right, where were we? We wanted to add indentation, which we do here. Yes, we do cast enums. This looks reasonable actually. So yeah, we created true false, we switch over the tag of this true thing, set the tag here, break. Yeah, that's it. Do we break here? We don't. Okay, this could have gone wrong. Yeah, basically here. Here we want to add a break. Okay, we have C code. That looks reasonable. I mean, there are still things we don't support. We don't support enums with payloads. You know, like tags. You can't even create them. And when we create them, we would also have to special case them in here when casting, because then we also need to carry over the payload to the new enum. But apart from that, this is fine. Okay, all right, concat is not implemented, which I guess is fine for now. Let's like I'm eager to try if this works, to try and see if this works. Yeah, some more indentation here, and then actually let's maybe output that to some file. So in breakfast, instead of just printing this, what was it? Read file, so we probably have write file, test.c maybe. Oh, thanks. With the C code. Cool. This call doesn't work. That's the signature. Oh, yeah, bytes. But we can convert a string to bytes using this. Okay. Wrote C code to test.c. Let's actually look at that. Yes. This is indeed C code. Now the moment of truth, and yeah, this won't compile on the first attempt. Yeah, exactly. Okay, so I see. So there are some errors, a lot of errors actually. One is, you know, we switch over line 81. Well, there are no lines here. Oh. Yeah, we need to switch over the tag. switch condition.tag. That's the one thing. The other thing is we saw that some functions are implicitly declared. That's because in C you can't use functions before they are declared, which we will need to solve somehow. I think you can like predefine functions or something like that. Okay, but the types work. That's cool. Okay, then we have functions. And this built-in function doesn't exist. But I think you can just, for example, declare a function like this. Yeah, you know, this doesn't hurt. And this means that you can use this function everywhere. So I think before even function, these are function implementations, but before that we also print the signatures, which will be a slightly simpler thing. So this will just be, you know, we take the signature, return type, we write the signature, write the parameters, closing thing, but then we don't write the body, but instead just have a new line. Yeah, so here we have the function declarations. That should be, function declarations. First declare all of the functions, then they get implemented. Okay, and this is actually another error. The value of int can't be assigned to an entity of type stuff. All right. Built-in compare, why does that return int? Wait, what? Oh, wait. This doesn't even exist, that function. Right, because it's missing the argument types somehow. Ugh. I mean, we know the argument types. We could just, build a signature on the fly. Okay, so when calling a function, should we do that in here? I think we should do that. Well, yeah, let's do that in here for now. We can still change it later on. Call with args, right? And the function signature is not just the function name, but it's actually a yogurt signature. Yeah, which expects the name and a slice of types. They're basically the arguments. Arg types is the vec of yogurt type, and then for arg in call.args do concat arg.type and push that to args types. Okay. So then here we can say arg types to slice, and boom, we have a yogurt signature. And then we can say signature.stir.mangle, which should contain the types of the arguments. Okay, another try. Yes, this looks like a function that exists. Beautiful. We can call. Whoa, there were no errors here. Hang on, can we just compile this? Okay, main doesn't work because it calls main int. And yeah, of course the signature of main is this right here. this main space int, and space is converted to 20 because in ASCII space is 20 in hexadecimal. Oh yes, beautiful, clean, readable C code. Wait, what's down here? Based on a, yeah, do that. No to do necessary. Yeah, but this is main that takes an int with a number of arguments, right? Whoa. Wait, so we can call this, and it called the function. Nice. What is the code currently doing? It prints, well, it returns some strings and then they are ignored. Sure. Sure. Let's maybe for example, in the false case, we can just crash. Oh no. Too big. Oh. I don't reference in crash, right? Crash is crash. I feel like I already wrote this too many times. Built-in crash with a message. Okay. So this casting to small a is not supported. Oh. Oh, indeed. Whoa. Yeah. Here we have a never. True, we create a crash. We have a crash function at compile time. String too big, we call that. This never returns. Then what does the switch evaluate? It basically doesn't matter what we write down here. But still, this should be correct. And I think this is actually the correct way to do this, because you can cast a never to every single type. You can assign never to anything. And we can promise this to the developers using the language, because we know that an instance of never will never exist. So yeah, if you give us an instance, which you can never do, we can cast that to anything. Right, which means in the C code we can just do nothing in that case. You know, casting from never is allowed, yeah. So if the target type, so the, not expression type, but, oh yeah, right, expression type. If expression type is never, then, I don't know, do stuff. Case never, we already write the annotation, so we need to write something here. Casting never do something. Yeah, I don't know. Something like this. Casting to small a. Oh, right, because the source has to be this. Right, so I was right. We need to have a separate thing up here. And we want to get the type of this. We need that anyway, right? Casted type. We could call that, you know, source type and target type, maybe, to make things more readable. Yeah, casting to target type is not supported. True. Cool. Source type is this. And here we can even say casting source type to target type is not supported. Nice. So basically what we see, if source type is never, then can we return or something? Well, yeah, we could just return. No, this is in loop. Yeah, but we can just continue. Okay. This seemed to work. Actually, let's see how this looks. Casting strings. Yeah, here. Cool. So when we have a Comptime string small, oh yeah, the result of the switch is Comptime string small. So here we create a Comptime string small and assign that to the switch result. And here we have a never. We crash this, and then we cast the never to a Comptime string right here, but we don't actually need to do anything because this code is never reached, because this crash always terminates the program. Okay, and I also really like how this Comptime string small is then used to how you crash right here with a Comptime string too big, but we don't actually create a string here, but this function is specialized to this type. So then in here we create a string too big and print that. Crazy. Oh yeah, printing is, this should look different. Yeah, printing strings. A string has a data and a len. I think in C there is no, they just expect null terminated strings. So we'll, oh wait, so this doesn't work now. We need to think what is the correct C code. We basically want to have something like this. Iterate over this and just print a character. Which character? Well, data I. Yeah. So let's do this. We have a for loop and then we print the character. And of course not 1, but this. And sure. We need more indentation and stuff. Oh yes, beautiful. Okay. Alright, and down here we only print a new line. This emits a backslash and an n, and then the C compiler will read backslash n and emit a new line. This, the stack of compilers. Oh man. Okay. Cool. Let's see how this looks. Whoa. No, this is not correct. Reload file. Yeah, don't save what I wrote down. Okay, yeah, I guess new lines would have been a good idea. Like this. Whoa. We want to crash, so we do this. We iterate over from 0 to the string length, print the character, print a new line, and then exit. You know what, let's compile this. ePrintf doesn't exist. Hate it. Can we just use, what's the way of printing the standard error? Oh wait, is it like fprintf and then standard error? Something like this, perhaps? No, sorry. Oh wait, standard error is always 1, right? Oh, no. Let's see. Works. Takes no arguments. Also seems wrong. How do you print C print to standard error? Fprintf, yeah. String and then where does standard error come from? From standard IO, which we don't currently, nope, we don't use that. Okay, so we could do fprintf standard error, and then up here what's standard IO? Let's sort these alphabetically. Okay, well, yeah, let's first compile this again, and then compile that C. Whoa, it worked. Doesn't do anything. Doesn't do anything. But if we have enough arguments, too big. What? Okay, we have a program. Damn. Okay, if you pass too many arguments, then the main function will print, hey, this is too big. That's so cool. Okay, so we basically achieved stuff. We can compile the program to C. And then use GCC to compile that C code to an executable and run that. That's cool. That is super cool. Okay. Yeah, I think that's it for today. I'm happy. This is a good state for the language to be in. Cool. Very, very cool. Yeah, let's maybe review this thing, but I mean, I've shown the compiler pipeline a lot of times already, so yeah, I guess that's it. What would be next steps? More error handling would be nice, you know, to get compiler errors that show you the line number instead of just saying here something is wrong in a file. Yeah, so that's probably what we'll do. Yeah, so I guess see you next time.